you got since 2000. Okay, since 2002. Sorry, but the main elaboration on the results was in the beginning of the 2010s, so 2010, 11, 12, something like this. But there will be a new mission or a new program, GRACE FO, and it should start, or it has started already in 2018. But I'm not sure if you can get data already from this. The resolution is also not very high, 153 kilometers. This is not very good resolution, but on the other hand, these data are very, very helpful, as you will see in the next slides. So the GOCHA is from the ESA, from the European Space Agency, and I don't know about the program at the moment, but we have talked about this with some guy from the ESA last year. I should recompile this. So you get data for GRACE, and they are for free, or yeah, I think they are for free, but you have to set there your email address and why you are using this, for which purpose, and so on. But this should be no problem as you are working in universities mostly. So this is for North Africa and the Arabian Peninsula, the results here, or some of the results that come up here. So if you do this over a long time, these gravity measurements, then you can derive fluctuations in groundwater levels, because groundwater influences, of course, the gravity. Yeah, and therefore you can say, okay, on the one hand you can derive from this the sediment thickness, but on the other hand also the fluctuations, and you can see if water levels are going up over long times, so over many years, or if they are going down. And this is very important for the resource of groundwater in general. But behind this you can also estimate via these gravity measurements not only the thickness of sediments, but also here the porosity and some lithological parameters. But these are estimations, and be careful with this with these data. But at least they will give you hints worldwide. I picked this here from this publication that is focusing on Northern Africa and the big aquifer systems there. So this is the Nubian aquifer system here in big parts of Libya and most part of Egypt. There should be also a big part of Sudan and Chad here, but on the other hand, this big northwest African aquifer system, which is in Algeria, parts of Morocco and Tunisia, and also parts there, the western parts of Libya. So this publication was focusing here, but there are worldwide also some publications about this, and perhaps it's a good idea to have a look at this. Yeah? Especially for the big aquifer systems, for instance, also the Ganga plains, it should be possible to work on this level. I doubt whether it is possible to work really in aquifer systems in Chennai. I think they are too small. Even also the Swarnamukhi or whatever rivers there, they are too small. The rivers, sediment thickness is not big enough it may be that the results are not so helpful. But for instance, in Australia and in South America and North America, the big aquifer systems there, it's very helpful. So here are worldwide results. Perhaps you have a closer look here at this publication. Yeah. Okay, other sensors work more on the atmosphere, not so much in the underground. And there is, you see here the tropical rainfall measurement mission. Oh, I have forgotten an E. Here in the measurement that is caring about tropical rainfall mainly, but you will get also data up to 50 degrees north and south, so it's reaching to Europe, also to southern Europe at least, not really to Germany or only the southern parts perhaps of Germany, but here, or the measurements are quite interesting. They are measuring precipitation here, and by now we have also satellite missions that measure wind velocities in different height, on different levels. So near ground or in the stratosphere or whatever. And this is very helpful for the weather forecast, but it should be also perhaps helpful to do large-scale estimations of groundwater recharge and so on. Yeah. Okay, so this is the precipitation, the rainfall here. A few images, you see this is from some time frame here, but you can get also, I think, actual data. Okay. Differences over time. Okay, if you want to look for this data, here is a quite interesting internet link, and I've proven this morning. It works. You can choose there, or you can find there a lot of data. Okay. Any questions up to this point about remote sensing and special sensors? As I said, especially for the big aquifer systems as the Ganga plains, the big artesian basin in Australia or the Northern African or also in South Africa. In the Namib we have a big aquifer system, not so as big as in North Africa, the Nubian, but also this, and also the Siberian and in Southern America. South America we have the I've forgotten the aquifer there. Sorry. We have also there two big aquifer systems in South America. Okay. So by now, yeah, it's. Let me have a look if we should start by now with this topic. Yeah, perhaps it's a good idea to continue here at this point. with the groundwater isolines, and make a break after these lectures. So the topic of groundwater isolines, it is quite easy, or of groundwater surface. We want to reconstruct, or we want to construct the groundwater surface from measurements, from point measurements. Normally we don't have any spatially distributed measurements. We only have point measurements, and from these measurements we have to derive our groundwater surface. Yeah. And the question is how to do this, and this leads also to the question of regionalization, which is a question going far beyond only groundwater isolines. But groundwater isolines are the first step for it, perhaps, because it's quite easy to understand and to see, and even if you have it only at one point at the wells, you can also imagine that it is, or you can at least measure this quite precise at one point. So we have two kinds of groundwater isolines in terms of time. On the one hand, we have a mean groundwater level or groundwater surface in a defined time frame, and on the other hand we have the groundwater isolines of one record day. This is not meant exactly one day, but several days are possible there, it should be around about one day. The question behind this is, or the topic behind this is, of course, the question of fluctuation of water levels, and in this in time. And this means we have to look for the input to that is influencing here the groundwater levels, and of course precipitation and the air pressure is influencing the water level, the groundwater level, and therefore we have to look for these parameters in the atmosphere. And there we see, at least in Europe here, that that we have, for instance, some low pressure and high pressure systems going through mid-Europe, not day by day and not over several weeks and months, as for instance as the monsoon may be. I don't know exactly how it is in Chennai. I think monsoon should be a little bit earlier than in New Delhi, isn't it? It should be in June already, isn't it? Monsoon time starts when? Or when is monsoon time in Chennai? Oh. Winter. It's Katikian helping us. Mrs. Anandarai. Southwest monsoon, okay. Yeah, this is clear. It's going southwest, okay. Okay. And which time? June to September, okay. Yeah, then I was right. Yeah, in New Delhi, it's more July to October. It's coming a little bit later than in southern India. Okay. Fine, thank you. So this is a long time frame where you have October, December, northeast monsoon. Okay. Okay. October. This is does this northeast monsoon also influence southern India? That would be also interesting. Or is this only in the north of India then? Small discussion between Indian colleagues. That's good. That's nice. That helps to understand. Northeast monsoon contributes to lesser percentage than the southeast. Ah, okay. Southeast or southwest. Okay. Okay. So it's a longer time of monsoon there. If you have June to September with the June to September, and then okay. So at least I know from the Indian colleagues in, but they are working. They were working all over India from Andhra Pradesh to New Delhi, in all this this mid to northern part, not really northern part of India, but southwest monsoon. Okay, thank you very much. They tell me always we have 3 seasons in India. We have winter, that is from October to around about December, January, and summer starting early in February, mainly in March, going to June or something, and then we have rainy. So 3 seasons, summer, winter, summer, and rainy. But of course, in Chennai, this is far to the south already. It is a little bit different, and yeah, okay. Thank you very much. So then you have a long time where you have a lot of precipitation, and this is reliable precipitation, and the water levels, the groundwater levels will come up during this time continuously. It's no good time to measure over a long time frame. This is where we started here with the record of a day. Here in Germany, we can say, okay, the weather conditions are stable for at least 2 or 3 days, and therefore we have to measure within this time frame if we want to have time fixed, or if we want to get a time fixed record. So also the surface waters don't fluctuate too much in such a time frame of 2 or 3 days. Normally, of course, we have also floods sometimes where we have within 1 hour rising water, widely rising water levels in the surface waters, but this is unusual, quite unusual. And normally we say, okay, 2-3 days are a suitable time frame for groundwater level measurements if we want to have a very time-focused groundwater surface. But also the mean groundwater levels are quite interesting and helpful, and very helpful, because they are used to outline, for instance, the catchments and so on. Of course, the basic information are the water levels at groundwater observation wells, and this is in most parts of the world a big problem, because nobody will drill a borehole or will drill a groundwater observation well somewhere in Africa. They will only drill wells for water supply and not for groundwater observation. And therefore, all these wells are normally closed. It is most interesting that I think most of the wells in the world come from India. The pumping wells, the hand pumps, they are coming mostly from India, I think. And they are used also in Africa somewhere, and this is very helpful. But on the other hand, they are closed, really closed, so that they are not contaminated, that nobody can fall in. The duck wells, on the other hand, they are big, but they are rarely available. How is it in Chennai? More duck wells or more bore wells? From my experience in Varanasi, for instance, and in New Delhi, they have more bore wells by now, but in former times, of course, duck wells. Bore wells, yeah, okay. That's also my observation there, and this is quite interesting. These wells are really closed, and this is good. And therefore, it's easy to take a sample there and to measure hydrochemistry, but it's very difficult to measure water levels. You don't get any information for this, and therefore you cannot construct your groundwater surface because you don't have the information of the water level here. So, the groundwater at the groundwater levels at the observation wells is one information. In Germany, we have much more observation. We have much more observation wells than wells for the water supply, really. But on the other hand, we can use also other information, especially the water levels of surface water. You know? And if you interpolate or regionalize the water levels from observation wells and surface water, then it's a good idea to subtract this surface from the surface of the ground, from ground surface. Then you see where you have made mistakes. Because you will have some areas with perhaps very high depths to groundwater, and this may be sometimes not reliable. And on the other hand, you will have areas where your water is standing 10 meters in the field, and where if you are standing in the field, see nothing of the water. And this is quite interesting, and it helps really to calculate the depth to groundwater by subtracting from the ground surface the groundwater surface and see if this difference is really reliable, so the depth to groundwater. There is a remark about this. Question: Chennai receive rainfall primarily from northeast. Okay. 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 So let's have a look. How to create such a groundwater surface. On the one hand, you should only look at the groundwater levels of one aquifer. Otherwise, you will get some gaps, some big holes in your groundwater surface and something like this, which you cannot explain exactly and in a very proper way. And to avoid problems there, please only use the observations of for one aquifer. It may be not the top aquifer. Top aquifer, of course, is most important for the plants, but it may be a deeper aquifer, for instance, for the water supply. then always only pick the wells of the deeper aquifer if you want to get the surface or the groundwater surface of the deeper aquifer. You should show also your area of interest. Okay, this is not so such a big condition here. Yeah, same height difference. If you draw lines, ISO lines, every or for each, let's say 10 centimeters, or for all for each meter or something like this. This is good, quite good, because then you see also where we have short distances between these ISO lines and where we have big distances. If you say, okay, in this part I will leave out these metric or per meter these ISO lines, and draw only the 10 meters and 15 meters, but in between I will let them end because they are too near to each other. Then you will get a wrong image in your mind, and also perhaps you may get wrong calculations afterwards. Same time frame. We talked about this already a little bit. So of course it's not a good idea to have in Germany winter water levels combined, or the groundwater measurements in winter time combined with groundwater levels in summertime. So for instance, at the end of April, or here in Germany, it is the most important time slots are at the end of April, beginning of May. There we have normally the highest groundwater levels due to the reduced evapotranspiration in wintertime, and therefore higher groundwater recharge over winter. And on the other hand, at the end of September, beginning of October, in October, at the end of October, beginning of November, half a year later, where we have the lowest groundwater levels, due to the fact that over summer we have a high evapotranspiration, therefore the groundwater levels are low. And but of course, in your case, pre-monsoon and post-monsoon are the most important time frames to measure. And of course, it's not a good idea to have pre-monsoon and post-monsoon data mixed in one groundwater surface for the construction of one of the groundwater surface here. So please have a look at this also. Catchment area should be shown, yeah, okay. Interpolation method. We come to this, or regionalization method. We come to this over the day several times, and we will see what methods we can use and which methods are most reliable and which we shouldn't use. Sampling points and supporting points. Yeah, this is very important. Of course, groundwater observation wells should be shown. Perhaps if you cut your wells and measure there, you should tell this also, and you should show your points of measurement also there. But also the supporting points that you get from the surface waters. Yeah? You should show them on the map, of course, with different colors or something. Or the observation was a little bit thicker and surface water a little bit smaller. It doesn't. It's up to you to create a map here. Yeah. So a little bit of process knowledge about this, about things. For instance, if you look at only one aquifer, you may have also perched aquifers. That means you have here some kind of clay or something in your sediment, and on top you have some kind of groundwater surface. Yeah, it's some kind of groundwater surface, but it is not the groundwater surface of the main aquifer. So therefore, a measurement here compared with these measurements will lead to completely wrong constructions here of flow directions and flow velocities and so on. All these things are then completely wrong, and therefore be careful to have really the or to take only the observations in one aquifer. Yeah. Another point is what is very often made wrong. Even in German big cities, even in Berlin, it was in a certain time frame completely made wrong. They have taken the depth to groundwater, or they wanted to create a map of the depth to groundwater. This is necessary, as you know from yesterday, the lecture, for groundwater recharge, but also for groundwater vulnerability, as you will see in the afternoon in the soundtrack lecture. And they wanted to create a map for depth to groundwater. And of course, the observation belts are always in the valleys. Who should drill in groundwater observation well on top of a hill? Yeah. We don't have high hills in Berlin, but it doesn't matter at this point. But therefore, they had, for instance, a well here and a well here, an observation well. Yeah, and then they have they have taken the depth to groundwater here and here, and of course here the depth to ground. If you interpolate this, then all over this area you will have very shallow groundwater, very near to the ground. But on the other hand, they didn't drill the well here because it is the depth to groundwater is very high here. Yeah, and if you neglect this information that you have a hill here in between, then you will also neglect the information that we have a high depth to groundwater here. Yeah, and therefore it's always necessary to take really the ground surface. It may be even the ground surface from the SRTM dataset, although you know by now it is not reliable, but it helps at least to get a first information or something. And then to create the groundwater surface, and then subtract from the ground surface the groundwater surface. Yeah, and then you get a reliable, or more or less reliable depth to groundwater values. Yeah, otherwise it's no good idea. Yeah, this is made wrong very, very often. It is a big mistake and really very misleading, especially for these maps of groundwater recharge and groundwater vulnerability. Yeah, but also for other, even for the water supply. This is very misleading. A big mistake. Okay, this we saw yesterday already, that we have here these isolines in purple I mentioned yesterday, of the groundwater surface here, the isolines for the groundwater surface in purple. Okay. Here we have it for Berlin. By now it's done correctly. Not only here in this quite new map with the groundwater isolines, but also the groundwater surface, the depth to groundwater is calculated correctly since 10 years or something like this, yeah, or more than 10 years. But in the late 1990s and beginning 2000s, it was done sometimes wrong. Okay, so we have here the map for Germany, and you see a lot of areas where we don't have any isolines for groundwater. Yeah, this is a big problem that we are on the way to solve here in our university. But these areas mainly have hard rocks where you cannot measure, where you will not install groundwater observation wells because there is no groundwater, or not much groundwater. Of course, there is water in the underground, this is clear. But as in the sandstones around, also in India, in a lot of, in big parts of India, just as there you have hard rocks where you hardly have any groundwater, some magnetites or some metamorphites. There you have hardly some groundwater, some gneiss or schists or something like this, and there are no groundwater observation wells installed. The question is, what do you do there? Of course, you have surface waters, and you can try to construct something from this knowledge. But yeah, we will try to find out ways to get also groundwater surfaces for these areas, and therefore also depths to groundwater and so on. So this is a little bit tricky. This is the same in India, not only in these areas where you have the hard rocks, the highly consolidated hard rocks with nearly no porosity, but in India you have additionally the problems that you have less groundwater observation wells. Yeah, and therefore it's quite a big deal and very difficult to create groundwater surfaces in India. Yeah, but also in Africa, this is the same. Okay, it's easier to create to regionalize some hydrochemical parameters, because in the wells, in the water supply wells, you have the water, you can sample and you can measure the hydrochemistry, but you cannot measure the groundwater level there. Okay, this is once again from these hydrogeological maps for the former GDR, so this is from the 1980s. But on the other hand, these are mean groundwater levels for this time, and over a time frame of 10 years, roundabout. And on the other hand, this is the topmost aquifer, and the influences after that are also quite clear. So that these maps, although they are quite old, they are very, very helpful. Yeah, especially for the German students, they should know about this. They are here. We have them. Yeah, not here in our university, of course. Not all of them for former GDR, but the geological surveys of the federal states, they have all these maps. Yeah, and if you are working in these areas in Eastern Germany, please ask for these maps, not only for the groundwater isolines, but also for parameter maps and so on. Yeah, this is very, very helpful. Also groundwater vulnerability maps, as you will see in the afternoon. Okay, so groundwater isolines, raster data. We need raster data handling here at this for the creation of groundwater isoline maps. But on the other hand, this topic we will focus after a short break of. Did you have a short break? Do I have to upload something? No, I don't think so. Okay, I think we should have a 15 minutes break, something like this. Ah, there is a question. Or something to tell me, or others. Mrs. Eckert. Why is this? Is that the former GDR has so much more mapped groundwater isolines. Yeah, yeah, the western part is also coming up by now. But in former times, especially before the European Community Water Framework Directive, the hydrogeological maps were not so much focused in Western Germany. So we had here and there some single maps of a few square kilometers with hydrogeological maps. Geological surveys in western part didn't focus so much on the question of hydrogeology. That's a pity, yeah. In the former GDR, it was, or the question of groundwater was very much, much focused in terms of water supply. And therefore, on the one hand, this was secret, so not everybody had access to these maps. But on the other hand, it was highly ranked. Water supply was a very important topic for the development of the former GDR. Therefore, these maps were compiled very thoroughly and very good on a very high level. This is the same with the water protection, not with the groundwater protection maps, this also, but with groundwater protection itself. They had very high standards, at least on the paper. In practice not, but on the paper they had very high standards. Higher than even in Western Germany, but also in other parts of Europe. Yeah. Especially there. In Poland it was not so high, and in Czech or somewhere else. But in GDR it was very high. Yeah. Okay, so we should have a break. 15 minutes, okay?
What can I do? What? Player one. Oh, good. Bunny. Players. Bunny. Bunny. More. Monkey. Stick. Ready. Move. Move. Great video. Yeah. I am a winner. Winter and a sun. A sun. And Yeah. Oh. Oh.
So back again. A little bit more things to do than expected. Okay. So by now we go to raster data handling, and yeah, first of all we have to create raster data. We saw already that we have the, for instance, the images and how we georeference the images. We don't have to do this with the raster data that we create by now. We don't have to georeference them after creation. But we can do this, we will do this already in a georeferenced way. We will create them. Okay, the question is how to come from, for instance, point data or line data here to the raster data. And if you look at these pictures, then you see it's not just a shift or a transformation. You can do this, of course. This is possible, especially in QGIS, but this will not be the result that you expect. Yeah, if you just transfer vector data sets with points, with lines, or with polygons to the to the to a raster data set, then only at only for those cells the value is set where you have where the observation point in our case lies in, and therefore we will not get a continuous distribution. The same with the lines. Think of having a channel network, a river network here, and there you see another problem. Of course, one point always lies in one cell. Yeah, this is clear. One vector point is either in this cell or in the next cell. Exactly. But with the lines, you run into the problem that one line, of course, will cross several cells in your raster, but on the other hand, it may also widen, therefore, our rivers or our creeks or whatever. Yeah, due to the fact that two cells adjacent to each other. Of course, here we have also two cells adjacent to each other, but that two cells so adjacent to each other that the river width will be changed, obviously, in the raster cells. This may also happen. Yeah, and therefore it is not as easy as just converting vectors to rasters. Here you see it even on a higher level, yeah, with polygons. The same problem, or some more problems than we saw already with the vector polygons we have here in the raster for the raster data sets. Now, for instance, this at this point here, this yellow area, it is connected completely to this area here. Yeah. To this bigger area here. And here, if we look at the raster result, the rasterization result, or the just conversion from vector to raster, perhaps this is important. Yeah, what can we do then? What would be first solution? Easy solution, very easy. That's right. That's the easiest solution. Of course, then we have a lot more cells. This is clear. This means more memory capacity, we need more memory capacity, and so on. But especially with our computers today, this is not a big problem. Yeah. And therefore, to improve the resolution would be the solution that we go normally at this point. But have a look at this. If your resolution, your raster resolution is high enough. Okay. The question is by now not just to convert from vector to raster, because as we see here in this picture, it doesn't help to convert the values, the water levels in the observation wells to a raster. It is nice to have these raster cells set with the observed water levels, but in the area in between, we don't have any information. So we have to use other methods here. And the way we do this is the regionalization. Especially if you want to calculate the depth to groundwater. We talked about this a lot, therefore I will not go into details too much. With the height data, I talked about SRTM data set. By now there is another radar mission going on called Tandem X. And this should give much better results, much better height results, but I have no experience with this. I'm sorry for this. I didn't download or order some part of the world. This I should do some time, but not for this short course. I think. Please have a look at this if you need this for your purposes, or if you think that it will help you. Tandem X should be better. Should give better height values than the SRTM datasets. Okay, so data collection preparation. The question is how to get all those measurements regionalized so that we have a complete groundwater surface, for instance. So we have several methods to so-called interpolate or regionalize. I prefer a little bit regionalize because it's going on regions and not just in some graph in Excel to interpolate from one point to the next. But don't care too much about this. This is a little bit a question of definition and how we talk with each other. And I'm not angry about colleagues who are talking about interpolation. And I will talk also about interpolation. I will mix this also during my talk here. Okay, so the question is how to interpolate, how to regionalize here. And of course we can take our measurement points and say, in the distance, on the distance between these measurement points, doesn't matter in which direction, we take half of the distance this value and the other half of the distance this value. Yeah, we can do this for all of our measurement points, and this will lead to so-called either Thiessen polygons or Voronoi polygons, or it may be called also nearest neighbor method, which ends up in the same picture in the end. Yeah. The result is always that we get discrete areas with a constant value around the measurement points. And then you, of course, get steps in your distribution. Mr. Billion, is there a question, remark about this? Okay, no. So we have steps, really steps in our distribution. For rice terraces, this is nice, but normally not in groundwater. Of course, we have no steps in groundwater. This is clear. This is one possibility. You know perhaps also the method of triangulation, and this is the most common method for groundwater levels. Yeah, we have our observation wells with water levels, and we triangulate between them, and then we have a continuous distribution or quasi-continuous distribution because we have raster cells. But quasi-continuous distribution here of our water levels, yeah, or in this case of the topography. Yeah, doesn't matter. So just to get you, give you an impression how the results look like. You see here some ugly triangles. This is not nice, but of course you can heal this. You can make it better by setting additional points or something. Here in the valley, we should talk about this, or here on top of the hills, we should talk about this. It's not that easy as it sounds, but it looks quite good. The next method that you may have heard of is the inverse distance weighted method. It's inverse distance, so the distance is in the denominator here, and we multiply here with, of course, z. This means the estimated value here, or the measured values in this case. For one raster cell, we take the distances to all of the measurement points. We square these distances sometimes, but you can also say, oh no, I don't want to skip a square. Or you say, squared is not enough. I take power 3 or power 4 or power 5 or something. Think about the results. Think what should be the reason for getting different results and so on. I sum this all and then I get this quotient. I sum this for all of the measurement points and I get the estimated value for one raster cell. This is not completely right because then you have always, or for each raster cell you get different weighting factors, and this is no good idea. So you have to divide it by the distances once again, so that you get always a weighting factor in sum of 1, so that all the weightings are the same. So this is the correct value here, or this is the correct formula. So the sum of 1 by d should be in the denominator, or should be calculated, and you should divide this here. Yeah? But it's a quite straightforward method. Just as with the triangulation, just as with the nearest neighbor method. All these three methods are based on the geometries. Therefore, I call it geometrical methods. On the other hand, these are, or in literature you will find two names for this class of interpolation or regionalization methods. The one is non-geostatistical methods. This is quite good, but there is also the sometimes you will find also the expression deterministic methods. Yeah? And this is misleading a little bit because, of course, the values between 2 points or 3 points or whatever is determined by the measurements. But on the other hand, or what you express also by this term deterministic is that in between the regionalized values are reliable, but all of these realizations here, nearest neighbor, as well as triangulation, as well as IDW, they have the same reliability between each other. You have an idea why that? They have the same variance, they have the same mean. Of course, it cannot be different. They have the same standard deviation, everything is the same. So statistically, none of them is better than the other. Yeah? There is no way in statistics to say this is correct, this is not correct, or this is better and this is not so good. Yeah? Statistically, no chance. At this point, we have the question, can we do something to get statistically better results in our estimation here? And we can. But on the other hand, this IDW is very helpful for the next step. I mentioned that the name for these methods is sometimes, or that these methods are sometimes named non-geostatistical methods. If we have non-geostatistical methods, then we have also geostatistical methods. Yeah? And this is quite interesting. So in QGIS, we have only two regionalization methods available here. Both are working with raster. So also the triangulation is not working with the triangles themselves, but they use only the triangles to set raster values. Yeah? So in the end of a triangulation with QGIS, you will not get a so-called TIN, a triangular irregular network. You can get this also via GIS, but you will get a raster data set. Yeah? Of course, according to the triangulation method, with the values according to the triangulation method. So we should have a look at this. But in SagaGIS, we have much more. Yeah? We have much more possibilities for interpolation or for regionalization. Okay, so I prepared a data set, a very high differentiated data set for Eschwege. This is with thousands of points. But I have also a data set for Berlin with groundwater observation wells. Fictive, of course. They are not there. You cannot take your bicycle and ride there and have a look at this. But they are distributed all over the town, and we should construct it perhaps, or we can create a groundwater surface here for Berlin. I think it should be a little bit more or nearer to application for this purpose of groundwater observation wells than the high density vector data or point data set for Eschwege. Therefore, I would like you perhaps we need also Eschwege afterwards. We should do it with Berlin. Yeah? Okay. So let's have, oh no, this is no good idea. I have to open my screen to you so that we can work together. So I'll remove here these layers. These nice layers. And I will open the layer of the observation wells. In this case, of course, it's in the folder Berlin, and there you have the GWM. In German, this means Grundwassermessstelle. This means groundwater observation wells, and I have made, or I have got from my database an Excel file. Yeah, and in this Excel file, you will see, or you can see. Let me have a look. Let me show you. We have X and Y values. Just as we imported them in the last days, especially yesterday, you can do this also here for, where is it by now? Oh, it's not there, it's here and here, no, here and we have it here. Yeah. This is what I got from the no, this is not what I got from the database. I got from the database only the CSV file. This is already with, these are the observation wells somewhere here to this point, I think. Yeah, it should be. Okay, we will see why I look so thoroughly for this. Okay, so I got some observation wells from the database system we saw yesterday how to get it, and I will pick it here with the GWM. No. Let's get to Berlin GWM. Shape. Okay, I open it, I add it, I close this here. Okay. there are already a lot more data than I thought. The question behind this is normally, or here in this data set, you have already the surface water digitized with the surface water levels. So it's prepared a little bit better than I wanted to do this. So it's perhaps in the CSV file. Let me have a look. Cancel, close. And let me have a look at the CSV file. At least there should be the only the observation wells. So it's okay. Point coordinates, x coordinate, point coordinate. Let's close and what's that? Perhaps it's due to the fact that I have a comma instead of a dot as a... I have to remove this. Perhaps it works also here in QGIS. So file format, record and field option. The decimal separator is comma. It looks like this here. I made this mistake perhaps. So you can you may substitute the commas by dots if you want to, or you may choose this option here. So if you set here decimal separator is comma, then it should be opening and close. Yeah, now it's there, but I don't see it. Layer CRS, and I set the layer CRS. It is Gauss-Krüger zone 4 by now. Yeah, so we are back in Berlin. So we have to set here the coordinate reference system 1 again, and then then it's there. So this is the trick here. If you call this, if you open this CSV file, that you check here that decimal separator is comma. Yeah, in Germany we use we often use comma as decimal separator, although this is quite unusual, of course, in terms of international or in international settings. But when I work at the Free University and when I do this course at the Free University, then all the computers there in the PC lab are set to German, have German settings, and there the comma is needed and not the dot as decimal separator. Yeah. Okay, but always also have a look at that you have the point coordinates and that you get the correct x and y field. Yeah, and here you should choose, or already at this point you can choose the correct reference system. Yeah, the CRS here. Yeah. Close, and then it's correctly here, yeah, and you see all the points at the surface water. I will pick here a map of
change the decimal system.
You saw how it can be done in QGIS, but on the other hand, you can do this by hand, of course, in every editor. Yeah.
Okay.
It's no problem, just by substitution.
But how does it work in QGIS?
You can. Okay. So I will open once again here this GWM.CSV. and show it to you. So we pick here In German. Okay. Okay. So I open this here and no, I made a mistake at this point. Of course it is. So Mr. Zentl has given you the hint already, but I will show it once again to you. gwm.csv, and there you have Daten format. There you cannot set this. This is the single separator. I don't know what is the header of this of these fields here, but in the second field you should find Dezimal Trenner, Komma. Datensatz und Feldoption.
I found it. Thanks a lot.
Yeah. So okay. So to set the correct coordinate reference system, please take it here. So please open this new window here via to select the CRS, and just filter for the DHDN as in the last days, and you will get all these 3-degree Gauss-Krüger zones. And Berlin is in zone number 4 and number 5, in our case in zone number 4. Yeah? Here for this case. Yeah? Mr. and Mrs. Manoy should find it, or you should find it also, isn't it? So if not, please filter for DHDN. Deutsches Hauptdreiecksnetz, and then you will find here within all these other options, you will find here 3-degree Gauss-Krüger zone 4. So the filter is quite helpful here, DHDN. Okay. I hope you didn't. You found. I hope you found it. Okay. I say close at this point because I loaded it already. So we want to interpolate based not only on the observation wells, but as I mentioned in one slide. Perhaps I find this slide somewhere. We use also the water levels here of surface water. Yeah? And therefore, besides the groundwater observation wells, we have to digitize also the surface water levels. In Berlin, it is quite easy. On the one hand, surface water is perfectly connected to groundwater because we mostly have sands, and even if there are no sands but some tills, the contact between groundwater and surface water is so good that we have the same water pressure at the same groundwater pressure as the water level in the surface waters. Yeah. This is the one thing. The other thing is it is made easy in Berlin because we have locks here all over the city, where the water level up and down of these locks is regulated strictly. Yeah, it's always held on the same level, so it's very easy for us. And I will show you in the background the map of Berlin once again. At least I will try this to find the topotype here. I made the mistake that I have to do something first. Something else first. Berlin, there. Okay. So I can. You have the topo TIFF. Hopefully it is. No, this is actually. Hopefully it is changed or you changed back the topo .tfw to its original name, yeah, then it works. But I'll show you close. So this is your map, your topographical map. I put it in the back and I will take out here this one. Okay, so if I check only the groundwater observation wells, you see, yeah, no, it's not good to see. Something like this. You will see they are, of course, not located in the rivers here, River Spree and River Havel, and also not in the canals, but in between them. So we have a lot more information. For instance, we have or I told you about the log. What's going on here? Why is this not coming back? Hello? I can't push around by now. I think there's something going on with the network, with the university network. Sorry for this. Oh, what's that? So, no problems there. Can close this once again. Out savings, no problem. No, I don't know where the problem by now is. It must be somewhere in the network. I hope you don't have these same problems. I have to kill my job by now. My QGIS job. Okay. On the other hand, it's not okay. So I have to do this once again. So I first load here my topotif from Berlin. I can use also the geological map of Berlin. It's also interesting to have it as a background map. So yeah, okay. So by now I get the observation wells, the groundwater observation wells. It's of course the text file here that I open, the CSV file. And once again, yeah, this is okay, this is okay, this is okay, okay. Yeah, okay, close. There it's not known. The coordinate reference system is not known here for the geological map, and I have to set it. And of course it is Lost River Zone 4, as I mentioned before. And I take this as the project CRS, and I will focus, zoom to this layer. What's it? What's going on here? Zoom to this layer and open again the topotif. Perhaps we get it then running. And close. Yeah, it is there, but but without coordinate reference system again. Set layer CRS, and it's possibly zone 4. And I want to have it in the background. Okay. So the next step for us would be, we don't do it, we don't have to do it, because I did it before and we have it here as a shapefile already finished. On the one hand, to export this GWM with our observation wells to a shapefile, but on the other hand, to add points on the rivers and canals. Yeah, I mentioned we have some logs. By now it works. For instance, a very famous log is here. This log is directly aside of the Berlin waterworks. So this is quite interesting. Another famous log is around here. This canal is very famous. This is the Landwehrkanal, and here we have the zoo in the western part of the city of Berlin. And there is a restaurant. This is the Schleusenkrug. This is very famous here. And a little bit downstream here of River Spree, we have another famous log here at a big castle, Schloss. This is Schloss Charlottenburg. There we have also a famous log. Another one is here. It's not here on our picture, on our map anymore. Schloss Spandau. So we have everywhere logs, and the water levels the water level upstream and downstream is always strictly regulated, as I said. Therefore, it's quite easy, and we can digitize directly the rivers and canals here, but I did it, as I said before. So we can load the result of this digitization as a shapefile here in our case. So gwm.shape.shp should be the vector dataset with the water levels here in the rivers, in the channel network, and I can open this. I can say add and close, and yeah, it has a coordinate reference system. Yeah, so Mühlendammschleuse, Bermachno is regulating here the log a little bit downstream from here. This is regulating here this canal, and on the other hand, Schleuse Charlottenburg, Landwehrkanal, Schleuse and Schleuse Spandau are regulating the water levels upstream here and downstream of the rivers. Okay, so I click out here the map, the topographical map, and we see here by now all the values or the points for the basic points for the interpolation or regionalization. If we look at the attribute table, it's quite simple. We have, of course, don't have all our XY coordinates. We may add these XY coordinates. It would be a nice idea, but what we have, of course, are our water levels here. Yeah, you see meters and N. We have there the water levels. And from the groundwater observation wells, we have also X and Y coordinates. Of course, we have waterworks in Berlin. No, not of course, but in Germany, this is quite uncommon that within a big city you have your waterworks. But in Berlin, it's the case. We have waterworks, and therefore we have very low water levels in some parts of the town or of the city. So this is quite strange or quite interesting. but we will not come to, or we will see this afterwards, but not directly by now. Yeah. So I mentioned in QGIS you have only the interpolation methods of triangulation and of IBW, so inverse distance weighted method, and we should look for this. Older versions, in older versions you have some button here in the menus, but in the newer version you need this processing toolbox. Perhaps you don't have it here on the right side as me. If not, go to processing, you have it up here in the menu, and then you choose the toolbox. If I check it once again, then of course it will be away, but I need it. So processing toolbox. Then you get this here. And you see a lot of methods that are available for raster and vector data handling and for file export and import and so on. A lot of tools are available here from QGIS. But you see you have also GRASS tools. We didn't work with GRASS up to now, and you have also Saga tools. Yeah? We will not use the Saga tools from here, but you can use some of these tools from here. It's not always possible, but sometimes it is possible. It is not working perfectly, but as I said, Saga is installed automatically on the Windows, and therefore you can use this tool also. It will be a little bit uncomfortable compared to QGIS, but it will work. With the GRASS tools it's better, nearly all of them are useful. But although you have, for instance, in the raster tools, you have the possibility of interpolation methods, also geostatistical, pre somewhere, raster, no. There should be also some other interpolation methods available, but be careful with this. These tools are sometimes working very slowly, and on the other hand, in a not so nice and handy manner as it is in GIS. Yeah? But on the other hand, especially some old formats are supported, data formats are supported, and there are a lot of possibilities that you have with GRASS, but sometimes it's also quite uncomfortable. So we first have a look at the QGIS methods, and in our toolbox you find also interpolation methods. Yeah? And you see, if you open this here, you have the heat map methods. I didn't go into detail with this. But you have IDW method and tin interpolation, yeah. And we pick here the tin interpolation, yeah. Of course, we will do afterwards also IDW, but first of all, tin. Yeah, this is most common for groundwater for groundwater levels. Perhaps in Berlin you do this also with by hand to interpolate with triangulation. Not for as many observation points as here, but for several, 10 or 15 observation points. Yeah. Do you do this, Berlin students, or do you do this in Chennai? Interpolate by hand? Of course, on a sheet of paper is clear, based on the map, triangulation or something. Yeah, triangulation only. Perhaps also nearest neighbor. How is it? Nobody talks by now. Such a long time ago. It was in the BSc. And you all came from other universities to Berlin, and you skipped the BSc in Berlin, and therefore also this interpolation by hand, isn't it? maybe. Yeah, okay. In former times it was, that's right. The hydrogeological triangle. This is the. Did you do this also in Chennai? Something like a hydrological triangle or a triangulation method at all, or the Thiessen polygons or Neu polygons? Did you ever hear of this or work with this? Not. Oh, that's a little bit tricky then. Perhaps I can show this to you, how this in general works, by using just some. So we have our measurement points somewhere here, and here, and here, somewhere here. Okay. So then we have to triangulate this. So we have to create triangles from here to here, from here. So like this. And if you have, for instance, the values here at this point, it doesn't matter if this is hydrochemistry or if it is the water level, doesn't matter. So for instance, you measure here 10 and oops, sorry, you measure here something like 12. Oops, come on. 12. Also over here perhaps the 12, and here for instance the 15. Then of course it is possible to use the distance here to this point, the distance to this point, and the difference here to say, okay, my isoline for 15 is of course going somewhere here, but the isoline of 14 I have here on this angle and here on this angle, and I connect them, and then I have 14 here and 13 the same. I measure it for instance here, and then I connect both, and I have then for instance oops, the oh, I can choose here this one. I have for instance the isoline of 14 like this. What's that? Okay, I've taken this one like this. The isoline of 13 like this. And 12 is of course like this here. Oops. And for 11 I have it here, and for 10 I have it here. Come on, I always pick this. Oh, sorry, this is wrong. Of course, 10 should be going here. Yeah. So this is then your these are now your isolines, due to the fact that you find these points. So that you find these points here on these, I think this is called angles. Yeah. here and here. Yeah. This is 11. Yeah. And here you calculated here this distance, you divided this by 3 because the difference here is 3. So in between, the first third is for the value of 14, and 2/3 are in 2/3 of this distance. You match here the 13, of course, and so on. Oops, what was this? Ah. Okay, here was the 14, and here is once again the 14 between these 2 points, and here the 14, oops, between the 13 between these 2 points. Yeah. So then you construct these orange points, and then you connect them and get the isolines, the groundwater isolines in this case. Yeah. This is triangulation, just geometrical value, and we will do this here. Yeah. Of course, this is then done automatically and not with not as I draw this here or picked out here in this graph with only lines. But if you think of having a raster in behind, then for all of the raster cells here in between, the values according to these triangles are set. Because also here you can calculate, according to a certain formula, the value if you have these measurements at the edges of your at the vertices of your triangle. Yeah. Okay. So we get a raster afterwards, not triangles. So double click on it, and the vector layer that we use is of course the GWM, and the interpolation attribute. You see also here the term interpolation is used and not regionalization. What we use is meter and n, meters above sea level, and but we have to add this here for our interpolation by this plus. Yeah? Otherwise it will not have the interpolation attribute. Yeah? Interpolation method should be linear in our case. The extent, yeah, the extent is a little bit, so we get afterwards a raster for a certain area. And of course, this raster is outlined in the end by the triangles, of course, and therefore it will not be completely filled. Here with this triangle method. With the IDW method, it will be completely filled. And the question is, how big should this raster be? We can define this. We can draw the extent on the canvas, but I will calculate it from my layer GWM. Yeah. Then we see, oh, okay, it will be 10 centimeter raster. Of course, this is ridiculous for groundwater observation. A raster size of raster element size of 50 meters, something like this is sufficient. Yeah. Then we get 343 rows and 393 columns, and of course, if you set this here to 100, then it will be even less. Yeah. Or if you set this here to 25, it will be also much more. Yeah. I think 50 is okay. And we save this to a temporary file, open output after running the algorithm. Yeah, it should go, it should work. Yeah, we run, and after a few seconds it's calculated. I close this and I see here, and I will put the GWM on top. I see here by now, okay, here we have some high groundwater levels. Here we have very low groundwater levels, lower than this lake here, This is due to the waterworks, and here also, but all around here we have normal water levels, just as the rivers and canals, whatever. And here, yeah, there should be also some waterwork. There is, of course. This is the waterworks Riemeister Fen, and here we have, which waterwork is this? Not Jungfernheide. I'm not sure. This is Waterworks Tegel. This is the biggest waterwork here in Berlin, with extractions of round about 800 cubic meters, 800,000 cubic meters per day. No, this is total. Sorry. No, it should be several 10,000 cubic meters per day that are pumped here aside of this lake here, Lake Tegel. Yeah. So a lot of groundwater extraction. In the southeast, outside of this map, outside the frame of this map, we have additional waterworks. And also up here we have one small, very small waterwork, but this is also not regarded here. Now we see, okay, this is quite interesting, and it works. Yeah. We will do the same by now with the IDW method. Yeah. We want, again, go here to the interpolation methods, and we say we want to have GWM interpolated. We want to get meters and n here as interpolation attribute, and we add this once again, just as with triangulation, also here for the IDW methods. And here we can set the how is this called? Distance coefficient. No, this is the power that you saw for the distance. Yeah. So distance or the squared distance we saw here in our. Where are my slides? So close the slides. Oh. So here in our formula. No, here is power 1, but here in the formula we saw this was power 2. Yeah. As I said, it's up to you to choose a suitable power here. Yeah. No one tells you. Yeah. There is no one who tells you it should be power 4, yeah, or power 2. This is just an estimation, and you can switch here from power 2 to power 3 or to power 1. Yeah, I will switch it here to power 1. Yeah, this very interesting. Yeah, once again here the raster cell size should be 50 meters, but we have to choose the extent. Once again, we choose it from the GWM. Yeah. And we get then these numbers of rows and columns again, and that's all. We run it, and we have a look at the result. You see by now, before with the triangulation, we had areas without values, especially here in this part, due to the fact that the triangles, or that there is no observation well here. Yeah. Therefore, there is no triangle around here. Yeah. So this is not filled up, or it is filled up by null values. With the IDW method, of course, you can also extrapolate to a certain extent, and this you see here. And you see on the other hand, this interpolation is the interpolation result is not the same. Yeah, it's completely different from triangulation. So at these points here, of course, in the cells themselves, we have the measured value as cell value, but directly around it, we have completely different values. Yeah, and this is quite interesting here. Of course, in for triangulation, also at the observation wells, we have the estimated values. Yeah, but for the IDW, this leads to completely different results. Yeah, only at these points here, for instance, here we have only in the wells or in the surrounding, direct surrounding of the wells, we have the drawdown of the cones of depression here in the cones that are resulting from the extraction, from the groundwater extraction. Yeah. So this is quite strange. We can also try to get the result for squared distances. So it's quite, no, not 10. We want to take IDW, and once again this meter and n plus, and we leave it here with the distance coefficient of 2, and we calculate from GWN and 50 meters once again, and we will see what will be the result of this calculation. Yeah, you see, this is a bit better. Yeah, in this case, you can try this with power 3. Yeah, and see if this fits more to your to the image that you have in mind. Yeah, as I said, nobody can say this is correct, this is wrong. Yeah? As soon as you don't measure, nobody can tell you. All these methods, and there are some more methods, some more geometrical methods and mathematical methods, all these methods are equally reliable and equally exact in interpolation. Okay, it's 12 o'clock already here in Germany. I would suggest to have a break at this point and to continue with the geostatistical methods after the break. No? So 1 hour of break. Oh no, there is question. I see there is question. There's someone writing something. Mr. Art.
I just wanted to know if it's a 1 hour break, like
yesterday. Yeah. Is it too long? 1 hour?
No.
Yeah,
I have to cook, so I need it.
Okay, you need the time. 60 minutes break. Okay. I will put it here so that you also all know. In Germany at 1 o'clock we will be back, and Mr. Zentl, did you want to contribute something?
Yes, if I do a different interpolation type, I don't receive new layer. It basically just changes the Interpol. Also ich kriege nicht ein zweites interpoliertes Layer dazu, so wie Sie. I only have the one that stays, and I think.
Oh, haben Sie vielleicht? So perhaps you have deleted the entry here. About that. There are a lot of things. So 1 moment, please. Yeah. So back again. Let's try it together and have a look if where the mistake was or where the problem was. So interpolation attribute is clear, and you should add it here. Yeah, this is clear, Mr. Zentek?
Yes. I'm pretty sure I did the form correctly.
You got okay, but you didn't get it. You didn't get a result, isn't it?
Yes, but I didn't get an error. It said it calculated it. I just don't, and I think my image does change, but it changes the already interpolated layer instead of creating a new one.
Ah, okay.
Now I have 3 separate interpolations,
Yeah.
and I can't get that.
Yeah. So in this case, perhaps it's a good idea not to save to a temporary file, but to choose here to save to a file. Yeah. Of course, you have to. Of course, you have to set the file name and the folder, but then it should save it there. Yeah. You got it?
I will try it 1 second. Thank you. I guess
Okay.
it's on the break already.
Okay. So then we'll meet again. Okay. After that. Thank you. See you later.
It didn't seem to help. Herr Gossel, sind Sie noch da?
So I'm sorry to be a little bit late back, but I uploaded in the meantime also the height data for Eschwege. I'm sorry that I didn't do this in advance, that it is not in your folder, in ESW folder. This was a mistake, but I think it's not too complicated to download by now this small zip file and unpack it in your ESW folder. So I just want to show it once again to you how we can do this with a big data set and what will be the result, why this will be, and how we will what will be the problems with these interpolation methods. You saw, or here in this, no, you don't see it. I just opened the screen here. Okay. So this is the data set I uploaded by now. So you see, on the one hand, if I uncheck here the height points, and I move one or the other layer. Okay. So here you see the lines, the ISO lines for the ground surface, of course, not for the groundwater, as they were in the topographical map, and very busy study. A student of us did it some time ago, digitized this some time ago, and yeah, you see, it was really homework for several hours, no, several days already. So it took some time to digitize all these height lines. From these lines we derived these points here, so they lie perfectly here, and of course they got also the attributes here of the height. So if you look at the height points, then we can see that there is the elevation here also. Oh, there are some lines with null values. That's interesting. Where are they? Not visible. Ah, they are there. Interesting. Okay, we'll see what happens with them, but it doesn't matter at the moment too much. So they got the values here for the lines, and we can now also interpolate this high resolution topography here. And of course, I will start again with thin interpolation. And of course, in this case, it's height points, all, because normally all these interpolation techniques work on point data, and it should be also in this case. No, it should be also in this case 50. Then it's quite fast. So the extent has to be set, and it should be from the height points all. Okay, I run it, and I say close, and this is the result here. Ah, okay. Quite interesting. The null value has or destroyed a lot here at this point. So we have to insert here a value. This also. Sorry. I don't know how it comes, but it is like this. Sometimes also there is another null value. Okay. So this TIM interpolation and also the IDW interpolation, this works quite fine. But as mentioned already, that they have the same statistics, so the same mean value because the mean value is calculated based on the sampling points. All the sampling points have the same all the sampling points are the same for TIN and for the IDW, and therefore the standard deviation, the variance, and the mean value is always the same. And yeah, by now it's time to reflect this and to see if we can get better statistics. And there was a nice guy. I also met him some time ago from South Africa, who said in the 1950s, and I think it was 1956, he said, there must be something better than the weighting factor of just inverse distance. There must be something better. He published this, but he didn't publish a method. He didn't know it. He didn't publish the method. His name was Krieger, as I said, from South Africa. And then a guy in France said, "Oh, that's an interesting idea. We should think about this." He needed several years. I think it were 8 years. And then he published, it was Monsieur Materon from the École des Mines, so mining school, let's say it like this, School of Mining in the, or near Paris, it's a little bit outside of Paris, I think. And he had a very interesting idea. He said, let's set up a diagram. Let's set up a diagram, and I will just continue with this small sketch here, but with all this deleted here. And in this diagram, we should have on the x-axis our distance between two measurement points. So here we have distance. The distance between two measurement points, and on the y-axis we should have the difference, or something like the difference. Not really the difference, but doesn't matter, as you will see, it doesn't matter too much. So we calculate between all of the measurement points the distances, put it on the x-axis, so always between two, of course. So if we have 10 observation wells for hydrogeology, then we have, how was it calculated? 2 by n minus 1. So we have around about 30 or something distances to calculate. And of course we can calculate also the differences in the values, in the measured values. So if we have at this point groundwater, so if we have here the 10 and here the 12, we calculate the distance between those 2 points, and the difference is of course 2. But Monsieur Materon said it should not be the 2, because if I calculate this way, 10 minus 12, it's minus 2, and this is not good. Because then minus 2 and plus 2 will give 0, and this is no good idea to have something like this. Therefore, he said, okay, let's take the variance. The variance of 2 points, the measurement of these 2 points. Of course, it's quite ridiculous. It's just the squared difference. So in this case, 4 divided by 2 by n. So this is the variance. The variance of 2 points is ridiculous. But it doesn't matter. It was quite interesting that he put this on the y-axis. So correctly, this would be the variance. Variance here on the y-axis, yeah. And then with several points, you get a point cloud. Yeah, this is clear. You get a lot, even if you have only a few points, then it is 2 by, n by, in brackets, n minus 1 divided by, oh, I don't know. Mr. Gauss knows it as a child. I'm sorry for this. I don't know it exactly. So you get a lot of points already, yeah. And this means you get something like a cloud, but this cloud is quite characteristic. Big points. This point is quite characteristic. It looks a little bit like this, normally. And he said, oh, no, there are a lot of measurements with the same distances and the same and nearly the same also differences. So let's take classes of distances at least, so that you get these kinds of classes of distances. And what's that? Too slow. I have to do it. And we find the mean here for these points within one distance class, and that makes it more feasible and more handy to work with. And so this should be the same lag here, the same distance here. We call this lag here, or this is called, today it is called lag. I don't know. I haven't read the original publication, I must admit. Okay. So we have these classes here, these distance classes, and we find the mean for all the points. And then this diagram is called a variogram. Yeah, variogram. And this is due to the fact that we have here the variance on the y-axis. Yeah? And it's quite interesting. Most of these variograms follow a certain path. You can imagine this also here. Of course, there are variograms that go up strictly, always go up. But most of the variograms do something like this. Yeah. Okay. That's just an observation. You'll see these are only the measurement points. This has nothing to do with some estimation. But Monsieur Materon said, okay, we need from these discrete points here within the distance classes, we need a continuous function to substitute in our IDW just the one by distance, this weighting factor, with the value here, yeah, or with this value multiplied by something, multiplied with the weighting factor according to the distance. Yeah, so the distance has, of course, an influence, but also this variance should have an influence. So we multiply the distance weighting factor and the variance here. Yeah. Sorry. Okay. This is quite nice. If you have, for instance, a raster point with a distance somewhere here, or something with let's say this distance here, yeah, oops. Then of course it is not the exact distance of from measurement point A to B or something, or 1 to 17. But in this case, we have a smaller distance and to the measurement point, and but we have also a smaller variance. We know this from this function. In between these measurement, this point cloud derived from our measurements. In between, we put a function, and we try to find a real arithmetical expression for this function. No? So that we can calculate the variance derived for this function from the distance that we have between raster point and the next, or some other, may also be here, some other measurement point. Yeah, not only the next measurement point, maybe also some other measurement point. Okay, quite a nice idea. And this method has some very interesting advantages compared to the other methods that we have seen so far, the non-geostatistical methods. By now we are entering the geostatistical methods with this variogrammetry here. So this, first of all, the variogram is set up by these measurement values. This is called the experimental variogram. Experimental variogram, these are the points. Experimental variogram. These are my points that are derived from the measurements. The line that we get here, this is the variogram model. Yeah? And believe me, there are people in the world that do nothing more than over the day, all the day, create variogram models. And they don't earn $5,000 a year, but they earn $100,000 a year. Yeah? Because behind this, you get, or they do this for gold, not for groundwater. Groundwater is cheap. Gold is expensive. And if you do this for gold, then there will be the big money behind this. And yeah, so. But on the other hand, in hydrogeology, this is very helpful, this method. And we use it very often, and we use it also for environmental purposes, yeah? To estimate much better than just with a tin or just with an IDW. Yeah? So I want to write down also here the names of both. The South African mining engineer, his name was Krieger, yeah, and therefore this is the method of Krieging. Yeah. It is not Krieging, it is not Krieging, it is Krieging, because the man's name was Krieger. And the guy in near Paris who developed the method, it was Monsieur Matterrand. Yeah? In errors. I will not write more down. Yeah. So this was in 1964, I think, and Krieger was in 1956. So this was the idea behind it, and let's have a look if this idea is helpful. Now, first of all, it is a nice idea to have it like this. Okay, let's continue a little bit with our slides. I always make the same mistake. So, no, I will come back to this here. So, we now saw what is the experimental variogram. If you do this variogrammetry for all the points in all directions, so from here to here you have a certain distance, from here to here you have a certain distance, from here to here. So if you don't look for certain preferred directions, then we call this an omnidirectional variogram. If we do this only for this direction, then of course we have only one point for this distance, but here we don't have any more points in this direction to calculate the distance and the difference. Or if you do this in this direction, then you can say, okay, I take with an opening angle not only these 2 points, but perhaps also these 2 points. Of course, this will be a different distance and a different difference. And we do it also for these 2 points, and then we have a direction where we get more points in our variogram, here in our experimental variogram. Yeah? These variograms that for which we take for different directions, these are called directional variograms, not omnidirectional, but directional variograms. Sorry, you don't see me. You don't see me. Sorry. Watching your virtual, I will do this again, so that you see me. Here you see, we can take this direction, then only here we have these 2 points, and they have no difference. So we get in our variogram only 1 point at 0 for this direction, with 0 difference, and but with a certain distance. So it's somewhere here, perhaps this point. Yeah? But if we take this this direction here, this direction, then we see, okay, with a little bit of opening angle, we have this point here with the 10 and the 12 here, and if we shift this direction, then we, with a similar opening angle, we get this point with 10 and this point with 15, and if we shift this once more, then we get also for, of course, this distance here, this distance is clear, but we get this difference between 12 and 15, so 3. So in this case, for this direction, we get perhaps 3 points here in our variogram. Huh? Yeah, you don't see the lines, that's right. Okay, let's right click on hide points. You don't see the lines, then you should, for this you should load the hide lines. I gave you 2 shape files, the one with the points and the one with the lines. Yeah? Okay. Thank you for supporting. High point. Okay, I missed all the all the chat here. Sorry for this. During my explanation, I didn't have an eye for the chat here. Sorry, Mrs. Wittmann, and thank you, Mr. Art, for helping us, for supporting here. Okay, so I hope this makes it a little bit clearer what a variogram is all about. And how it is constructed. The question of why we will focus in the next slides, of course, and where we can use it for. Okay, back again to the slides. So we know by now omnidirectional variograms in all directions and direction-specific variograms, as I said, as I explained by now, for these two directions which were rectangular to each other. From the first one, you will not get, for the first direction, you will not get any reasonable results, but for the last for the last direction, you got several points for your variogram analysis. So let's continue with the variogram analysis. We know also by now what the variogram model is, and we have at least a short idea what we can use it for. So let's have a look at the model parameters. We somehow have to create let's continue. We have to fix somehow this shape of the curve. Yeah. And therefore, we use predefined curves that need some parameters. Yeah? Some curve shapes we can fit to our experimental variogram. So these black points here are the experimental variogram, as I said, with classes, and for all the classes the mean. This line here is the line of the variogram model. Let's have a look at this a little bit more in detail. So there seems to be a point, at least up to this area here. Beyond this, we have, once again, a strict line upwards. But at least up to this point here, up to this distance, because this is connected to a certain distance, where we reach and where all the variances are around a certain level. And this is called the sill. This is the value up here. We see the sill has a variance of, in this case, around about 70. Yeah? Okay. We can compare this sill also to our general statistics of the data set. Which value should be the same as this sill? You got an idea? Write it in the chat. It's very easy. It's obvious, nearly. Which value of the general statistics we should compare to this sill? The mean? So on the y-axis, we don't have the mean. Therefore, it should be the, and now in the chorus, all together now, the variance, that's right, all together the variance. Thank you. Yeah, the variance, so we, it's preferred to plot the variance into the variogram here, because then we see if the sill is near the variance or if the sill is much below. It is interesting. It may be that the variance, the general variance, is up here. Yeah? For instance, if this comes to another sill, to second sill here, yeah? This may be. And this is interesting. If I have a sill much lower than the general variance up here, then this means the variance here in my variogram is lower than the general variance. And this is very tricky by now, because if the variance of my geostatistical interpolation, because I use this variogram model afterwards for the geostatistical interpolation, if this variance is lower than the general variance, then I'm statistically better than the interpolation of TIN, IDW, nearest neighbor, whatever you take. Yeah, because your statistics say your variance is lower. Therefore, your estimation is statistically better. Interesting topic. So, our variances of the variogram model, they begin sometimes with 0, but sometimes they may also begin with 25 or something. This means, within a distance of 0, we have a certain variance. This is critical, because this means you have a borehole here and you have another borehole directly aside of it. And the variance between those two measurements, hydrochemical measurements, water level measurements, whatever you take, this difference, this variance, is not 0. So directly aside of your first borehole, you have a second one, and this will have a differing, or may have a differing value. For groundwater levels, this is not easy to understand, because normally if you drill a borehole here and 1 meter side of it, what should be the value for the groundwater level? The same, of course, no question. But you have other parameters. For instance, if you look for the environmental geology, for instance, the PAH, the polycyclic aromatic hydrocarbons, where you have no mobility, where you have no transport. And therefore, these PAH are more or less fixed to organic matter in the underground, and then they are not distributed anymore. And then you may find with the one borehole something like a nest of this PAH, and directly aside of it, 3 meters away or 5 meters away, you will not find any PAH. And then you have something like this. If you do this with gold, you drill for gold in a certain gold for the gold mining, as Mr. Krieger did in the 1950s. Then you find with the first borehole, you find a nugget, and directly aside of it, you will not find the gold nugget, because the gold nugget is very small. Yeah? And therefore, this effect is named nugget effect. You have a variance, although your distance is very small. Yeah? It's quite difficult to understand or to transfer this to hydrogeology, but it is possible. So normally, especially for groundwater levels, the nugget effect should be 0. And you can set this also for your variogram model to 0, because you know there is no nugget effect. And if the experimental variogram tells something else, we have to look for this, but it is not possible. Yeah? If you think of hydrochemical parameters, for instance, distributions of main components as sodium or chloride or sulfate or something like this, then of course you haven't got any, normally you haven't got any nugget effect. But if you think of the EH of the redox potential, then of course during pumping you see this already. Yeah, when you pump, you get water from somewhere else. You take water from somewhere else. You attract it to your extraction well, to your pumping well, to your sampling well. And this means the water comes from somewhere else, and it may be that there is a nest, for instance, of some organic matter. Then you have a completely different redox potential than in other parts of the aquifer. And if you sample exactly at the point, if you sample exactly the water that comes from this nest with organic matter, then of course you will get this wrong, or this only for this point suitable EH value or redox potential. Yeah. Therefore, the redox potential may have a nugget effect. Most of the main components not. Electrical conductivity of the water, no nugget effect. Yeah, so you always have to think about the parameters that you are estimating. You have to think about the variogram, especially the variogram model you create, if this is suitable or not. So for this variogram model, we now know, okay, we need a nugget effect to fix the point where it crosses the y-axis, where we have distance 0, and we need the sill. Yeah, but we need also the point, the distance where this function enters this horizontal, this horizontal line, where it enters our sill in the end. And this distance here on the x-axis is called the range. Yeah? As long, so normally we would think the sill would be the base variance of our whole complete data set. So the sill, or we should compare this, and if it is like this, it's okay. If the sill is much lower than the variance, it's very good. But if the sill is in the range somewhere around the base variance, it's okay. But what is very interesting, as long as we are within the range, we have variances much lower than the sill. And this means much lower than the base variance, normally. And this means, okay, as long as I'm within the range around an observation well, my estimation with this variogram model is statistically much better than the estimation I do with, for instance, TIN or IDW or nearest neighbor. And this is a very interesting point. Yeah? So the range has a big importance. We should also create a map of the probability due to the factor of the range of the probability that my estimated value is correct. Yeah, so we get two maps. On the one hand, the estimated values, it is nice. According to this variogram and the weighting factors for the, of course, based on the distances for the raster points, for all of the raster points, of course, weighting factors for the measurement points. Yeah? We calculate the estimated value. So this is our first map. But the second map will be the probability, or something like the probability that my value has a higher probability or lower probability, or not lower, but or has a higher probability than TIN or IDW or some other methods. You know? So interesting, these geostatistics, yeah. And believe me, there are a lot of people doing such a job. Not a lot, but some people are earning a lot of money only doing this job all the time. And for us, it's very, very important to know about this method, because contaminations in groundwater can be estimated via this method. Much better with these geostatistical methods, much better than with TIN and IDW and everything. Yeah? Okay. Some curves here, some shapes of curves. The mostly used shape of a curve is this spherical model. Yeah? You see it's going nearly linearly up, then then it has this curve, and then it goes into the horizontal of our sill. Yeah, this is for roundabout from my experience 80–90% this variogram model is suitable here. Another one would be something like this, a linear variogram or a linear function here, and then when we come to the sill, then a horizontal line. But on the other hand, from my experience, I quite often find also a behavior like this here. This is the Gaussian variogram model. Yeah? That we start slowly with low differences in the small distances, but then it's rising strictly and more quickly than the spherical model, and then it goes also into the horizontal. Yeah. So this I observe often in geological structures, and this here in parameter distributions. Okay. Questions? Always ask questions via the chat if you have them, if they arise. Okay, this is quite important to understand. On the other hand, you over the time will get also some experience with this, and the more you think about this variogram, the variogram model, and what you are doing here, the deeper you get into this this question of interpolation or of regionalization here. Yeah. Okay, here are the functions for the variogram models. This seems to be very wow, the Gaussian. Wow, what's that? It is very easy to model to handle this also in Excel. It's no big problem. You just have to look for this a little bit, and if you have a closer look to this, then you see, oh, quite easy. Yeah. Okay. This is once again here the the way we come from the variogram model to the estimation of the spatial distribution. Spatial distribution, we do it today and the next week and in the next days only 2.5 dimensional, so we have only XY coordinates. But it is also possible to do this in XYZ coordinates, plus measured value, of course. But you have to think about a little bit more about what you are doing there. Because the heterogeneity or the variogram in the end reflects the heterogeneity to a certain extent. And the heterogeneity in horizontal dimensions is of course completely different from the heterogeneity in vertical dimensions. Yeah? And therefore the variogrametry, of course technically it's no problem. It's just calculating the distance from 3 coordinates. It's no problem at all. But on the other hand, the question behind this is going deeper into hydrogeology and geology, and therefore these methods are mainly used for 2.5D. That means you can interpolate over a surface. Yeah. Okay. So the variance is normally symbolized with the gamma. So these gamma values we know here. Yeah, these are the gamma values, the variances from point 1 to point 1. Of course, if we have no nugget effect, if the nugget effect is 0, then this gamma, this gamma, this gamma, and this gamma will be 0. Yeah, if we have no nugget effect. If we have a nugget effect, of course, we put in here the nugget effect. No, it's no problem. And we can also derive the gamma or the variance between point 1 and 2, point 1 and 3, 1 and 4, and so on and so on. So this is quite clear here, these gammas. These gammas are also quite clear because point P is in the end our raster point for which we want to estimate. It needn't be a raster point. You can calculate, or you can calculate especially the variance for any point in your area. Yeah, this is no problem. So these gammas are known, these gammas are known. The problem is that we don't know about the weighting factors, and the sum of all weighting factors here, W1, 2, 3, and 4, the sum of them all is or should be 1. So that not for the next raster point we should get another sum. Otherwise the weighting factors will be not consistent. But this is just a matrix calculation. You have the unknowns W1, 2, 3, and 4, and you have all the knowns gammas. You know that from the variogram model. Okay, so matrix calculation, this is known. And you insert another 1 and 0 to get an estimate for the range, for the probability map that I mentioned. Yes? These W's are unknowns and these gammas are knowns. So you have a calculation, matrix A multiplied by vector W gives vector B. Of course, this cannot be solved in a way that you divide vector B by matrix A. This is clear. So you have to multiply with the inverse matrix, and then you get your weighting factors W. Yeah. And this you insert then to estimate your value for the raster point. So a little bit tricky in calculation. And you should restrict also your matrix so that you not use all of the points, because as you have seen by now in Eschwege, there may be a lot of points. If you have a matrix of 100,000 by 100,000, then your computer says what have you drunken? So I cannot do this. I will, or we will meet again tomorrow, or in the next days. This should be restricted to, of course, the nearest neighboring points. This is clear. So normal or a good number is, of course, a dozen. So around about 12 points around, or 20 points around, something like this. You fix the distance within which the measurement points, the observation points are regarded. Yeah. You say, for instance, yeah, within 1 kilometer or something, if you look at the observation points for groundwater. Okay. Results. Let's compare this. Here in the upper left map, you see on the one hand, and this is most important here, you see the values, the measured values. And if you take the IDW method, then of course the measured values will be held. You will observe in the estimation at the measurement points also the measured values. You will get the same values there. But in between, you see here the lines of your estimation. Okay, inverse distance. Yeah, it's not so smart, so it's a little bit rough. But this may be correct. Yeah. Let's take the triangulation down here. The picture is not so rough and not so diverse and so as with the IDW, but it's angled and okay. Then there is the method. Then there is a part of methods that is called either polynomial regression or polynomial regression, or it is called spline methods. In the end, this leads to the same point. That means I try to develop a polynomial function that reflects best my measured values, but it will not fit directly to the values. This is clear, because you try to do this with a polynomial, with an arithmetical function, and nature is not arithmetical function. It is something irregular, something that has heterogeneity and so on, and therefore these spline methods or polynomial regression functions are allowed to deviate at the measurement points from your measurements. And this is a question if you want this. Therefore, I would not recommend to use polynomial regression or the spline functions. And in the upper right corner, you see the result from kriging. You see it is quite smooth. It is as long as you have zero nugget effect. You have no deviation from the measured values. But if you have a nugget effect, of course, the interpolator can say, oh, I want to create a smooth surface, and you allow me with the nugget effect, you don't know about mismeasurements or something, you allow me at zero distance that I have some difference, to get a smooth surface, I will override this measured value by another value that gives a better surface. So be careful with the nugget effect, but have a look also on the range and on the sill. So it's quite tricky, and to get a good distribution, it is and a good regionalization. It is a little bit of work to do, and you see this also from my explanation by now. It's not just clicking some buttons and then you are there. we will see how it works if this works in general, and how it works in not in QGIS but in SagaGIS. Okay. I don't see any questions. Enter the microphone or open the microphone and ask questions, or write it in the chat. So let's have a look at the tools that we have, and there I go back several slides to this slide here. We have a lot of several software tools for this geostatistical interpolation, but some of them are useless, or you can't use anymore. And the first two are of this kind. So this means GOEs from US EPA, so the US Environmental Protection Agency. This is a nice tool, but it was meant for DOS. I think there is also a Windows version by now. But perhaps it opens also only a black window, and within this black window you can work with GOEs. The same, but GOEs has one big advantage. The regionalization method, the geostatistical method, is explained technically on a very high level. So you know, or you can read in the manual what a variogram is about, how this can be constructed, and how this influences your estimation afterwards. Yeah. So GOEs, no software tool to use. There is only the possibility for 1,000 input points and 100 by 100 raster points. So this is ridiculous and nothing, not useful anymore. It was developed in the 1980s, and it was a good tool for, or at this time it was a good tool, yeah. Windows was developed in 1991, I think, and since then GOEs has not been updated, something like that. Easy kriging, also there, the manual is very good. So this is the estimator for Z. Yeah, easy kriging it is called. Easy kriging manual is very good, but also there the software itself is outdated, and I wouldn't use this here. The mother of all geostatistical interpolation is this book, because you will find also a book, GISlib, and the library. So this is a geostatistical library from Deutsch. He is from the École des Mines also. So he is originally from Paris, but he now works at the MIT, I think, or Stanford. No, I think Stanford. And journal, journal. Journal is from Paris and works in Stanford, and Deutsch is in Alberta, I think, in Canada. Sorry, this I mixed up. So the GISlib, it is a library. It is a geostatistical library. That means you have a lot of programs, and they are very efficient. They are covering a lot of topics in geostatistics, going also beyond the 2.5D geostatistics in terms of 3D geostatistics, in terms of variogram models, and everything very good elaborated. And therefore I recommend this very much, but only for advanced users, very advanced users. The book, even I will not read it. Yeah, it's all too difficult. A lot of mathematics and all these things. I'm a user and I want to apply this to a certain extent. But these code library, this can be bound together, for instance, with Python programs, to get PyGSlib. Yeah, and then you have on the one hand a graphical user interface, perhaps. I don't know if PyGSlib has a graphical user interface, I think so. And you can use all these high sophisticated methods, which are programmed in Fortran, to interpolate with and to get very good results. Yeah, this is quite an interesting way to, or a tool to interpolate here. Worldwide, the mostly used software is Surfer from Golden Software in Colorado. And this software is very handy, it's up to date, it doesn't cost very much. This all is for free. Here, Easy Cleaning, GSlib. GeoEase is open source, especially GSlib is open source, and it is for free. Also, for if you want to input or if you want to import this into commercial software, it is for free. I think the GSlib is also imported in the software in the in ArcGIS in the 3D analysis, no geostatistical analysis, of course. I think it is used there also, but of course with a lot of things around. So Surfer, not expensive, it's quite cheap, it is very fast, it works on a very good level here. Yeah? A very handy level. You have to look for some tricks, but we will not go into detail with this at this point here. So the geostatistical analyst with ArcView or ArcGIS by now from Esri, it is also recommendable. It is a very nice tool in terms of variable analysis and all these things. Very good, but it costs a lot more than the Surfer. So Surfer around about 300-400 euros or dollars, and geostatistical analyst 1,500. Then I would recommend for 3D a few tools. They are also freeware or open source. So open source is SADA, a spatial analysis and decision analysis tool, or something like this is the shortened. It is a shortened form for this. It is from a university in US, and you can interpolate 3D, and you can also visualize the results, prove the results. It is not very handy. It is quite good, but it is it is a software tool that has sometimes some problems, especially with very special graphic cards and so on, because 3D visualization is not as easy. Okay, then we have fields, which is nearly the same as SADA. Also the visualization, it's completely the same, but fields has a connection to ArcGIS. Fields is from the US EPA, I think, the Environmental Protection Agency. Yeah, they work together with the university. I think it is Tennessee here, University of Tennessee, and you get this connection not for free. So fields. No, it is for. Sorry. Fields is for free, but of course ArcGIS is not for free. And so this connection, it's nice if you have ArcGIS, because especially fields is for environmental purposes. That means you have also the limits for certain contamination parameters. For certain, let's say, take the PAH, you have the limits in the US. Implemented here in fields, so it is automatically comparing PAH values that are estimated in 3D with these limits, and you will find an isosurface with all these for these limits. And you know where to dig, and you know where to take away a little bit of soil and so on if you use fields here. Yeah? completely different is SGEMS, Stanford University. Geostatistical modeling system. No, I'm not sure about this. But SGEMS is also for free. It is very handy, but a little bit tricky. Yeah, it is. If you open it, it looks quite good, other than Zara or especially GeoEase Easy Cleaning or GIS Lib. It looks very handy, but there are some tricks in handling this tool. And but on the other hand, it's the most sophisticated. Yeah? Whereas Zara and Fields are more or less for environmental topics, SGEMS is a more general tool. Yeah? It also has 3D visualization and everything, and yeah, you should have, perhaps, if you are interested in things like this, you should have a look at this. It's for free, you can try it and work with it and see what you can do with this. In Saga and GRASS, you have also geostatistical methods, but be careful, it's only 2.5D, like Golden Software, or like the surfer here, or the geostatistical analyst, and it's not on this high level as the geostatistical analyst. It's a little bit comparable to surfer, yeah, but not as good, and especially not so widespread. The use of it is not so widespread. But we should have a look at this with our values here. So this we had already. And, where was the... Oh, okay, we stopped here. So Saga tools, we should use Saga tools. GRASS is too complicated, and it will calculate a variogram not for a certain range or for a certain number of neighboring measurement points, but only for all of them. So it will take long time, and it is not optimized in terms of calculation of with a lot of kernels in your CPU and so on. So this is not helpful. GRASS I will not recommend. It is not usable. QGIS has no geostatistics. SagaGIS has a little bit strange variogeometry, but we will see how to work around this and how this will work. One thing I forgot. R has a package called RGstat. And this is very efficient on the one hand, it is very sophisticated, it is very good, and I can recommend this also. It is also for free, of course. Our package, it's for free and very helpful. The connection to SagaGIS and to QGIS is very nice. So have a look at the internet, there are videos explaining this. And but I will not go into R by now because this will lead us to other software tools, and it will be too much for our course, I think. Okay, we should by now interpolate with geostatistical methods our groundwater levels. Perhaps also the ground surface. I've also uploaded, I think, the ground surface, the GOK, and we can use this here. So, in the software tools I mentioned, everything okay, we can go into work. Yeah, by now you know about this here, and no, we don't use surfer. So, here's once again the picture with the locks. Everywhere where you have a change in the color, you have a lock, and these are the water levels here in Berlin. You see, this yellow is 32.2 meters above sea level, and so on. So, yeah. But this you have in your shape already. But perhaps in a project you should have to digitize points along these canals or these rivers on your own. You know? And please do this. Don't forget it. Okay. Stationary sandwiches. Yeah. Okay. Okay, yeah, this is the next step. But we should have by now the opportunity to interpolate with geostatistics here in our course. Okay, I'll open my screen again, and we do this here. So, as you know, here you don't have geostatistical methods. Perhaps it's possible in this new version to use Saga methods here. So this should be, of course, within geostatistics. You have here no, it's not in geostatistics. Here you have only variogrametry and a lot of things around variogrametry, but there should be somewhere there should be. Is this? No. Okay. So we'll not do it here in QGIS with this Saga tools in toolbox. Raster. No. Okay. No, we will not do this in QGIS. I close this completely so that but I will do this in GIS. So I made a small button here on my desktop. And GIS. I just open it. At the moment I don't see your chat. But I don't see that you have any questions. Please, if you have questions by now, or if it's too fast, please do it via microphone, or ask me via microphone. So, on the other hand, we will go step by step here through the interpolation, to the geostatistical interpolation. So, start up project empty. And you see here the graphical user interface of Saga is a little bit strange. And the handling is not straightforward for a Windows tool. It is not as handy as QGIS, but on the other hand, Saga has a lot of advantages compared to QGIS or to other GIS, even compared to ArcGIS. Because especially here in terrain analysis, we come back to this point afterwards, we have a lot of modeling techniques, especially also in hydrology. Also for this we will see one or the other method here, and you see there is also for the morphometry and for profiles you have possibilities. We come to this in the next days, and a lot of modeling possibilities that are not available in ArcGIS or in QGIS. So in our case, the nice thing is Saga was originally already programmed for work with shapefiles and with diverse raster data formats and also other vector data formats, but shapefile was the normal data format for vector data. So we can open here in the upper left corner our shapefile. So it's of course not here, it's somewhere here. I have to scroll down a little bit here. It's in Berlin, in the Berlin folder, and we pick here once again the GWM shapefile. Yes, these are our observation worlds. We know this already, and we know how it should look like. Oh, something is done here, but at the end it's okay. Yeah, okay, but we don't see anything. No, that's Saga. So it's a little bit strange here with Saga, but it doesn't matter. We will see how this works. So the way to visualize your data is here via data, and or you go to the tab data here. You may also go to maps, but no, not to maps, to data. So there you see, okay, it has imported or it has opened our GWM, it seems to be, and as we know, these are point data, and we can visualize this by double-clicking. Yeah? Then we get the map here. You can also load background maps or whatever, but it's always a little bit tricky here to get the right formats and something. So Saga GIS is not really handy, but it has a lot of possibilities. Okay. So we know our data set is there, it is readable, we see our data set, and it is also nice if you want to plot something like this. In Saga, it's not possible. Okay, let's go to the tools, back to the Tools tab here. And there we see Spatial and Geostatistics is quite a good idea to open for instance, kriging. Yeah? And there we see we have several krigings. There is not only one kriging. I have shown you only the simple kriging by now. The background is that if you have a trend in your data set, then of course this trend leads to a distorted distribution of your data. And then, of course, normally you should not interpolate with this because your statistics is distorted. It is not a Gaussian distribution anymore. Kriging is very calm with this. You can do your simple kriging, but to be sure that you subtract the trend, you can take another kind of kriging. There is on the one hand ordinary kriging, which subtracts the trends internally, and on the other hand you can take also universal kriging, where you get also, at least in the original version, the trend surface, you get it also in an arithmetical function. We will not use universal kriging here and not simple kriging, but ordinary kriging with the external, with the internal reduction for the trend surface. This is very good, suitable, and Surfer, for instance, doesn't have simple kriging and doesn't have universal kriging, and but in ArcGIS you can also choose. But for our purposes, it's quite good. We can also create first variogram, but with ordinary kriging we have to go through the variogram also. So double click. This is also quite strange. A new window and it looks completely strange. It doesn't matter. We take our point set here. We take our meters and n, meters above sea level, and this is the most important thing already. And so let's go step by step through it. So type of positive measure should be please one moment.
Okay. Let's go.
Okay, I'm back again. Really, a colleague wanted to talk about an Excel. Okay. Standard deviation is okay. Logarithmic transformation. This is very interesting. Some of the distributions are distorted to a certain extent. They have skewness, especially, and then you can. Then there are several tricks. Of course, you can use a distribution like Weibull or Gumbel distribution to fit your data set to another distribution, but then you have to recalculate it again according to this distribution. A little bit tricky, but possible for surface water. Sometimes this is suitable and necessary, and they are very fond of this, but in geology, I don't know if somebody of you heard Gumbel distribution or Weibull distribution. A very suitable transformation is the logarithmic transformation. With this logarithmic transformation, you have a lot of advantages. Yeah? First of all, you logarithmize your values. And think of having, for instance, the hydraulic conductivities. Yeah? Especially for hydraulic conductivities, a logarithmic transformation is very, very helpful. Because if you interpolate just with the hydraulic conductivities, then of course you will get, due to steep angles, somewhere an undershooting. That means you get values below zero. Of course, this is ridiculous. You cannot have hydraulic conductivities below zero. This doesn't make sense in any way. But if you logarithmize first, then of course all your hydraulic conductivities are negative. But even 10 power minus 50 is positive. Yeah, so if you interpolate with the logarithmized values, you will avoid undershooting. Yeah. On the other hand, as I said, the statistical distribution, the probability function, will be more a Gaussian function, and the hydraulic conductivity are normally not normal distributed. Yeah. And so this is a second argument. So we have two arguments already. And the third argument, especially with the hydraulic conductivities, is that you are, if you are working in the field and you are doing a pumping test, you clearly can say this is 10 power minus 2 or 10 power minus 3. But you cannot say it's 2.1 or 2.2 by 10 power minus 3, let's say it like this. Yeah. So our perception in the field, or our field tests, are also giving us a feeling more or less for the logarithmized values, and not so much for the linear values. Although, of course, Darcy's law is linear, there is no discussion about this. Okay. So in this case, with the groundwater levels, we should not transform logarithmically. Okay, target grid system, user defined. Yeah, we should define here the cell size. We have taken 50 meters, and it will be a squared raster. This is a little bit, yeah. You may create also in other ways rectangular rasters which are not squared, but it doesn't matter in this case, especially in our case. We can here fix the x and y, the coordinates, the extent, and okay, columns and rows are automatically calculated. Everything is okay. Okay. Here, this is also quite interesting. So As I mentioned before, you can take all of your measurement data. In our case, this is suitable. It is possible to calculate with all of them, but if you think of the Ashwege data set, then it is not possible. Then you can fix here either the number of points that should be regarded, maximum, minimum. If you have less than the minimum input, then you get a null value. So perhaps this is no good idea to have it here with 16, but it should be perhaps with only 2 or something. Maximum 20 is okay. And here you can, and this is a little bit a disadvantage compared to Surfer, you can only choose all directions or quadrants. You cannot calculate according to certain directions. Would be a nice idea for an extension in QGIS or in SagaGIS. Yeah, you can program this on your own. So the search range is another possibility to restrict the number of points that should be regarded or that should be used for the estimation. So 5,000 meters is quite far because we have by now here, so it's these are 14, 16, 18. These are 20 kilometers and another, let's say 18 kilometers or something in north-south direction. Yeah, it may be 2.5 kilometers or something. So I insert here 3,000. Yeah. It should not, the range should not be, or not the range, the search distance should not be too big. Otherwise you will get a lot of point data that have to be calculated here. It doesn't matter in terms of computing time, although this is only running on one channel, on one thread, but it's quite fast nevertheless. We say okay, and then we get, of course, come on, the variogram. In this case, we have a linear variogram. Yeah? And this is not nice. We can also create shorter lag distances here. Yeah, this is done by settings. There you can set the lag distance, for instance, to 100 meters. Yeah. Maximum distance should be also reduced, not to the whole diagonal, but perhaps to half of it, so let's say 7,000 meters. Yeah. Okay, let's have a look if by now we see a little bit better the experimental variogram, but on the other hand, this is not the best variogram. I didn't remember this. I didn't set up my data set accordingly. Okay, let's leave it here with this linear variogram, yeah, because this fits very good to our experimental variogram. Normally, or in this case, or here you can choose the functions. Yeah, there are predefined functions, but you can also down here define your own function. And this is most important if you, or this is very important if you want to use, for instance, the spherical variogram model. You remember that we had these functions here in one slide, yeah? And you can use these functions here. Not directly, you have to transfer it to these parameters that are given here. Where is it? Where is the slide? Here is the slide. Yeah. You can insert, for instance, this model here, or this model function here from the spherical model. But we leave it here with the linear model. and we say, okay. And then it's running, tool execution succeeded. Nice. Yeah, down here you see it. Down here you see tool execute. But where are the results? Yeah. Once again, we go to the tab data and we see, ordinary kriging. Yeah, it's there. And then double click, either we can create a new map or we can put it on top of the map here. Doesn't matter, I take a new one. And this is the result then from the kriging. Yeah. So up here something strange has happened in the north here, but on the other hand, all the other parts seem to be good. And down here in the south, there are not enough data. So there we have null values or no data values. Yeah? Also here and here we have some gaps. So we should reduce perhaps to 1 minimum, in the minimum, and on the other hand we can also extend our search radius. Yeah? These are two possibilities. The question is, how do we get this here perhaps to QGIS or to something else? Of course, to QGIS. And we can go back to tools. And now we can export, for instance, or we can on the one hand, we can save directly here, right mouse click and then save as, but there we can save only as a Saga grid, yeah, as grid. This will be read also by by QGIS, no big problem, but to be more general, we should export it to another. Where are we by now? Here. So we can export it also afterwards. I would save it like this first of all, so that we can visualize this in QGIS afterwards. But it's more handy to export your grid. For instance, either to S3 grid, S3 ArcInfo grid, or to Surfer grid. Yeah? I would recommend one of them. But you can export also to XYZ. And this is a big advantage here of Saga GIS compared or another advantage here compared to QGIS. These two, or there are a lot more, especially ASCII data sets or data formats supported than with QGIS. Yeah? The Saga grid itself, it's a binary data format. Okay, we export it as an ArcInfo grid, as one example. You see once again this nice window. Of course, we pick by now here what is available, and we say we want. We click here into this field to get this file selector open. Strange, but it is like this, and if you know about this, then it's quite easy to handle, but you have to know about this. So, file selector, and I go once again to this folder, and we'll see afterwards what is the result here, what these ASCII files look like. Yeah. So these are the GW surface. Yeah. Okay, save. It's ASCII. The signal separator is now point, not comma anymore. Okay. So it's exported by now, it's saved, and we can go back to QGIS because QGIS is much more handy. You can print with this and everything. So QGIS, and we first of all get our data set here. It's not in Eschwege, it's in Berlin, and we have here our GWM shapefile. Okay, open. And, okay, close. So this is where we started. And now we pick here the raster layer. And there we see, on the one hand, we have this S-grid, here, S-grid, but don't open the the .sgrd file, but the s.dat file. Don't ask me why. Yeah, it is like this. It is like this, and please open the s.dat file and edit and close it, and now you are there. Yeah, push it around here. But you can also open your ASCII grid. Yeah? This was called GW surface. There. We have also a project or a projection file and the .asc. Yeah, we can open this, add this, close, and we see this is on top here. Yeah, it is on top. It is the same as the results are the same. No matter. Doesn't matter. The advantage of the ASCII grid is that we can read it. And we should open it to see. Oh, I should have this folder open already. And we can open this with a plain editor. Yeah, I open this with Notepad. Notepad is fast. If you want to have to get a real fast editor, the VI, in this case for Windows, it's the WinVI, is a very fast editor. It's very small. You can't get bold letters or italics or whatever. This doesn't matter, but it's fast and it reads. It works with really big data sets. Doesn't matter. We take Notepad here, and you see you can read it. Yeah, and we can analyze this here. So in the first row we have the columns. We have in the second row the number of rows and the lower left corner. This is quite easy to read. Cell size also, yeah, okay, fine. No data values, we have them also here. And then follow just for the first line. This is one line. One value after the other. Yeah? If you export Surfer, it's nearly the same. The header is a little bit different, but these are also only 6 lines or something. But the difficulty is with the geographical lines, we count from south to north. And with the image lines, we count from north to south. And Surfer counts from north to south, and ASCII counts the lines from south to north. So if you want to convert both data formats, you have to shift the lines. You don't want it. You are happy that you can read this file and that you can work with this file if it's necessary. Yeah? So, okay. Thank you and bye-bye. No. But this is the main thing I wanted to show you for today. Yeah? On the one hand, we have gone through a lot of raster data handling today. We have started with the okay, there is a question. May I inquire which Saga version you are using? Yeah, of course. But I have to look. It is coming with 3.18, I think, about Saga. So this is 2.3.2. But this is a very tricky. This is very tricky because you will find also Saga 7 point something in the internet. But this version 7 point something is much older than this version 2.3. So this is a chaos. This is really chaotic. And you see this here is from, no, 16. It's from 2016 here.
Well, to be fair, I had less parameters to enter, and my image looks exactly the same. So
that's good. So which version are you using?
Sorry, yeah, 7.9.
Yeah.
7.90. So I guess I will change to the one you mentioned.
Yeah.
2.3.2.
Yeah.
But I mean, it all worked the same, and there were less things to input. So maybe it's easier, but maybe I just got lucky this time. I don't know.
But perhaps you don't have these nice tools, modeling tools here, not here in spatial and geostatistics, but in, for instance, here simulation. You see here, you can do some erosion modeling. You can calculate fire spreading, hydrology. You see here, yeah? And the Saga is continuously developed, and especially they focus on modeling here. Yeah, of course, this is GIS modeling. It is not numerical modeling, but it is on a very high level. Yeah, and it is very, very helpful. We will see this also by now. We will come to especially terrain analysis a little bit here. Yeah, have a look at this. Yeah. So it would be helpful. So for instance, we can also, by now, yeah, perhaps it's a good idea to, I didn't open my, missed, I opened it, but now I closed it. So once again. Perhaps it's a good idea to see what we can do with such a raster. What will be the advantages and what will be the methods that we can use here from Saga GIS. And we should do it perhaps with the, either with the height data set from SRTM data set, or we should do this with an interpolated surface of Eschwege. Yeah, we will see this later on. So please have a look at this if you have these topics here available. Is it? I will have a look at the chat.
Yeah, that's available. It was more of the, once you clicked something, there were less parameters sometimes. Like I couldn't set a minimum value, for example, only the maximum.
Yeah, then it's good. Then it should work. Okay. So let's have a look. Or are there any other questions? Any more questions?
I would have a kind of off-topic question from earlier. I was wondering if there's a reason why most of the water is being pumped near Tegler See instead of near Wannsee, where I would have expected it to be.
Yeah. Yeah, the reason is that the Free University found out that in the pumping galleries along Wannsee, they get water not only from the Wannsee, of course most of the water is coming from there, but also from the opposite side of the Wannsee. And this means on the other side there were the Rieselfelder. There were these wastewater treatment or this land treatment of wastewater, and therefore there was part of from there came some contamination. And this was very interesting. Therefore, the pumping galleries on the eastern side of the Wannsee, they work and they get also clean water, no problem. But there was the danger that if you increase this number, if you increase the extraction there, you might perhaps drag especially trace metals into these into the wells on the eastern side, from the west to the eastern side. So the this land treatment of wastewater, this was the Rieselfeld Carolinenhöhe. So it was a little bit tricky. On the other hand, Tegeler had also the problems with the phosphate in it, and yeah, but this is solved by now, I think, due to the extension of the wastewater treatment plant in Schöner Linde. The problem has been reduced in the Tegeler See. They don't need the phosphate elimination plant anymore, and the phosphate has gone down. Phosphate concentration in the Tegeler See has gone down. This is what I know up to now.
Thank you, that was very interesting.
Welcome.
I too have a question.
Yeah.
When I do the ordinary kriging, it seems to have a lower resolution than the image you were getting.
Okay, yeah.
I think I did something wrong with the parameters.
Yeah, there is one step that you missed. I think this was the step where to insert the cell width. This is after, no, it is before having the variogram. Then you have to set the parameters for the cell width also. How to import kriging into QGIS. Yeah, we will do this again by now, shortly, because you by now know most of the steps already, and you will see, or you will focus certainly on these topics where you have the problems by now. Okay, so we will do this again, and for this I would recommend, or I would emphasize to use the point data set of Eschwege. Yeah, so we will not do it again with here this groundwater observations in Berlin, but for the Eschwege dataset, yeah, for the surface, the ground surface in Eschwege. So I go to Eschwege dataset, and I pick here the height points or shapefile. Yeah. It has to read a little bit. It says, okay, our data are visible only in the tab Data. Double click on it, you see, oh, a lot of data, a lot of points, really a lot. But also there we have areas where not so many points are. You know? These are areas where we have, for instance, mining. In this case for gravel, but this doesn't matter too much here. Well, we should by now continue with the interpolation. We go to Tools, and there we go to not terrain analysis, of course, but spatial and geostatistics and kriging. And I once again do the ordinary kriging. Yeah, double click on it. I say, okay, points are not set. Okay, I will take the height points and not the ID. No, it should be the elevation. Yeah? Standard deviation. Okay, no logarithmic transformation. Once again, for hydraulic conductivities, it would be very helpful. Here, not. Target grid system, user defined, is good. Cell size. By now, it's given 15 meters. This is too high resolution, in my opinion. I set it to 25, and this is for Mr. Alt, the point where perhaps you missed the input of 50 that we did before. Because there was in the original version, when we did it with the groundwater observation wells, there was 390 or something like this, or 93 or something. So this there was for the groundwater observation wells a very big value, and this was not good here. So please substitute this with 50. In my case, by now we have a lot more points. In my case, it would be, or the 25 is okay. So these are around about 800 columns already. No, 480 columns and 625 rows. It is quite a lot to calculate. You know, you have to calculate such a lot of raster points then. So search range should be, yeah, the 300 is quite okay. Minimum, or let me take a little bit more, because in the valley here, here in this area, there we have bigger distances to the next neighboring points, and I don't want to get too many no data values here, so I set this to 700. Yeah. This I leave as it is for now. I hope that you have seen that you see by now what parameters have to be inserted, where you can, so you can change also this here, of course, to get another extent for your calculation or for your bid afterwards, but this is not most important, or in my case it is not important. Yeah, of course you can do it like this here, 0, 0, and this to 700 here, to get round values. Yeah. And this to 50 here, and this also to 50, yeah, something like this. Yeah, so that you get round values. Okay. Now it calculates the variogram, and here you see, yes, there a spherical variogram model would be very nice. Yeah, would be very nice. Gaussian, here this doesn't lead to a Gaussian to the Gaussian variogram model. I would prefer here a spherical. But as I said, to insert here the spherical variogram model, it's a little bit tricky. You have to set up the whole term here. Perhaps it's easier to work here with predefined functions, and of course it is here. I know it is not. It is not. So it is quite nice to have this squared function, but it should be better to use here really a spherical function. But what is most important, we can leave it with the squared function, but what is not correct and what I will not use is the nugget here. Yeah, it has a nugget of 1000, and this is not helpful at all. Therefore, I kill here the A plus, because then it will have to be, yeah, it should be fit to the 0 nugget effect. You know? Yeah, I can get it like this a little bit better. Yeah, the most important thing is, or the most important part of our variogram is, as you have seen it before, and as we have learned by now, the part up to the range, what comes after the range doesn't matter, because you have here it is not, you don't have the no, I don't see it, settings. No. Okay. You haven't got the possibility here to insert the variance, the base variance. Yeah, this would be nice. But you know, if this is your sill, or if the base variance is here, somewhere here, maybe here with this 8,800 or something, then especially the range up to this sill, this is very interesting. Yeah, and this means all the function behind it, this is not so important. And therefore, I fit this to this first part here of my variogram. I fit the variogram model to the first part of my variogram. It is not nice, and you can do it better if you want. Me, I will not do this. I'm just lazy. Okay. Now it calculates, and of course it will take a little bit more time here than before. But on the other hand, it's finished already by now. And I can have a look at this, the new map, and you see, oh, it's quite nice. But I didn't. So the search radius was not big enough. Yeah? Therefore, it's a little bit tricky. No, I have to do it again. Sorry. So I will kill this. I will tell you later on why. Okay. So I will do it again. So this is all clear. So I will extend this to 1,000 meters, and I will reduce the minimum to 1 here. Okay. Once again, the variogram fitting. It has seen this. Okay. Oops. Okay. Okay. I hope I know it works. Yeah, it's filled. Okay, the problem is, on the other hand, if you don't fill, if you have here in your grid afterwards several no data values, then you can not work with sophisticated modeling tools. Yeah, you have to get a good grid to work with. Yeah? Okay. So up to this point, I think it's quite straightforward, or you know this by now, how to do this. And to get it to QGIS again, I will delete this here. Otherwise, we will have to switch here between the coordinate systems, and there will be some problems. And to get this to QGIS, this was also one question of you. I just go back to tools, and in my I always want to export this, not just to say. On the one hand, you can save this directly here. Hide points. No, this one. Save as. Save it as Saga grid, and then it's okay. But I prefer to work with ASCII data formats, especially data formats that are very common data formats, and therefore I use the option to import or export grids. In this case, I want to export the SVR info grid. I have only one grid. Okay. So to fix the file, I click here, and then I can use the file selector. And of course, I will not save it in Berlin, but in Eschwege. And it's not the groundwater surface, but it's the ground surface. Surface, yeah, that's okay. Now, ASCII, for, yeah, everything okay. I say okay. Now it's there, and or it's exported, and I can open it via or in QGIS. Ground surface is there, and I have to pick the ASCII in this case. Yeah. If I exported this Saga grid, this SGRD, then you cannot open the SGRD. You can only open the SDAT file. Yeah, SGRD is just a description. QGIS doesn't know about this correctly, and therefore you will get an error message. Now it's there, and you can work with this, create your maps, everything what you learned on Monday for the layout and everything. Yeah. Okay. So the big advantage, as I said, with GIS is it is also capable of geostatistical interpolation, but the big advantage is that we can work with this interpolated surface. I just have a look at the comments here. I'll try that. Did I miss something? This how to import query. So I don't know, Mr. or Mrs. Kirtan? I don't know. I hope you found it. Yeah, is it okay? So as I said, with the S-grid, you will have some problems. You can save it as S-grid, but then, okay, fine. Okay, let's have a look for the possibilities to explore or to work with this data. And this is very nice, as I said. On the one hand, for instance, if you go to I think it's simulation. No, it's in terrain analysis. Then, yeah, there you have also the possibility to calculate lighting. Yeah, for instance, for big wind power stations, you can see also then where can you see this, the visibility, or some flowers in the ends or in the Himalayas, when will they get a shadow, when will from the next mountain, when will they get sun, and all these things you can calculate with this here. Yeah. But of course we will not do this. This is not our topic. Our topic is, for instance, the channel network. Yeah. And this is a little bit tricky, because in the end, if you have, I think this, yeah, if you look very closely to this result here, then you'll see here in the middle, you have something like a hill in the middle of the valley. Yeah, and we can look at the results here. So if we go around here, I think, yeah, it's like this. We have here Z, no, where is, yeah, no, okay, no, where do we get the values? Normally I get down here the Z values of a grid, but I don't know. No. I have to end some action. I don't know which action. This is the action button. Okay. I go here to... No. I don't get the Z values. Why that? Will execution succeeded? No action anymore. But I don't get any information about this here. Once again, perhaps no. No, I have to end the action again. What is that? It's action. Okay. Let me get it here. One moment, please, colleague. So back again, but nevertheless I don't know how to get the Z values here by now. Okay, so sometimes the interpolation result leads to closed valleys. So we have to correct all these we have to correct here to fill so-called sinks. Yeah, if we have sinks somewhere here in our interpolated surface, then we should correct this. And this is done, or this has to be done before you, for instance, calculate the channels or whatever. Yeah, therefore, I would suggest to use here in pre-processing, the field things methods in pre-processing. Yeah, this is the thing, or this is something you have to do first. Yeah, I'm sorry for this. A method that works quite well is the method of Planchon-Darboux, but you may take also these one removal methods. The simple removal doesn't work so good. So, on the other hand, there is also some parameter that has to be calibrated, and which we cannot see in advance, but this method here of Planchon-Darboux, this works quite well. So, double click, once again, we pick that what is available, and the minimum slope here, this has to be, I think, I will try it with this here. This has to be set, and I don't know how it will work together with the results that we have by now from this interpolation. I say OK, and it will create here a new raster file. Yeah. So we will see. OK, we will see. Hopefully, see the difference at some points. Yeah. For instance, here we see a difference between both distributions, slightly different, slight difference. Perhaps I want, or in this case, for this year, I want to create the channels, yeah, the channel network. And this is done here in the terrain analysis with the filled sinks with the channels. Yeah. Then we can take channel network. A lot of things to set, but it's not difficult. So first of all, the grid system, it is the same for both, but the elevation is set not by the ordinary kriging, but with no sinks. Yeah. Flow direction, we should get also from no sinks. Channel network has to be created, also the channel direction, but what has to be set, and be careful to do this, is the initiation grid. Yeah? Otherwise it cannot start somewhere. Divergence you don't have to set. It's good to set it, but you don't have to set. And I think the tracing rate, this is quite interesting. You can also set the tracing rate if you have, for instance, a distribution of your precipitation. Perhaps depending on the topographical height or whatever, west wind drift or whatever, or the monsoon. So this is a weighting factor from another grid that you can load here. I will set this tracing rate not, because I don't have it at the moment and it's not necessary for our task, but it's possible. Okay, I think this should work. We will see. Okay, and it takes some time. Now finished. Once again, we have to get there, and channel network, we want to see it. First of all, no, it didn't work. Okay. Yeah. We have a little bit of problem with this, with these artifacts here, and I don't know where they come from. Also, even here in these areas. Okay.
It worked for me.
It worked for you. That's good. So I will close this here and try to do it once again. So everything here is okay. So perhaps I have to reduce the segment length. But perhaps you also don't have these artifacts. This may be the reason. I reduce it here to 3, let's say it like this, and perhaps it works then. Let's have a look. Yeah, by now it worked, at least a little bit. For the most important parts it worked, and we should have a look by setting it upon or on top of the topography here. This is done at this point. You don't have to calculate it again. At this point, if you choose, for instance, one of the maps here, yeah, okay, And then you see, okay, here it worked in certain parts, and there it worked quite well, and we can use these parts also afterwards. So here it worked, here also in these creeks, for these creeks it worked, but somehow in the middle it doesn't work. I don't know why, but it's very interesting for me, and we can do another, we can use another possibility to work with this result here. Yeah. So I have a look at the complaints. Okay. Anybody else who had problems?
Well, I see a full grid system, but I have no idea if it's accurate. And one thing I do notice is in the middle, there's a bunch of rather straight lines. So I think there's a high error going on there.
Yeah. So if you do this, we can do this also by importing our SRTM dataset. Yeah, we can do the same method again. And there we can see what are the problems with this SRTM dataset. Can you please explain channel network again? Yeah, of course. Okay, we will do it with a completely different dataset, but we will come back to this result here with another method. So I will import by now SRTM data, the height dataset that we saw already in the morning. And this we can get via import here. So we pick here our import-export function, and of course in tools. Yeah, this is clear. So we want to import a grid, and in this case it is not the SRTM30 because we have 3 arc seconds, but it is USGS SRTM grid. Yeah, it's a little bit tricky. I'm sorry for this, but it is available here. Yeah. So I will open this height file, this .hgt file, of course not in Berlin but in Eschwege. I have this .hgt file. I say open, 3 arc seconds, okay. I say okay. Full execution succeeded, so it's imported, and I have it here. Yes, and it's here, there it is, new one. So these are our Harz mountains, as we saw it already in the morning, but in QGIS, sorry. Now we have it here. And here the channel network works, yeah, but not the best. But we will see this. So we go to tools again, and we go to channel network again. Double click on it, but now we have to change here to the another nice thing for today, for the evening. Another nice thing. So this here, you can do this also with the other one. So we have created by now a surface somehow, and we can create by now a 3D view also of it. Yeah, and we have to set the system here. So we take the no sinks and resolution. Yeah, we can we can take another exaggeration. To our eye, normally the exaggeration in the mid-range mountains, an exaggeration of 5 to 10 is okay. So I would choose here 5. So this is the 3D view, what I've taken here and what I've picked here. And now I want to visualize this and say okay. And now you have a nice view, only of this part. You have a nice view on this area, yeah. But you can do this also for the whole area. Yeah. This is something for grandma. Or for your professor. When I was studying, I also created this was in the late 1980s. I created a 3D view of my mapping area for the geological mapping, and the prof embraced me and said, very good. But of course not with Saga GIS, but with Surfer GIS, with Surfer, and it was of course a little bit more tricky than today. Okay, no, like this perhaps. Yeah, 3D view, but in this case it's the only the ordinary kriging and without no things, and I like to get an exaggeration of 5 again, and okay, come on, and I have this nice view here of my area, and I can do this also with the Harz Mountains. Of course, this is no question. I will not do this. We come back to the channel network. Sorry that I'm jumping from one to the other by now, but I wanted to show it to you with this 3D view here. Yeah. So back to the SRTM dataset. If you want to do this with the SRTM dataset, it is a little bit tricky because in XY direction you don't have meters, but you have degrees. And 1 degree, we learned, is 111 kilometers. So going from 1 degree to the next is 100 kilometers. Therefore, the exaggeration should not be 5, of course. The exaggeration should be something like 0.0003 or something like this. So very reduced exaggeration. And if I take this here, okay. It was too much, even this 0.00. This is, the Harz Mountains are not like this. Okay, so this was just a little bit, no, I want to do it a bit better. So I want to show it a little bit better. 0.0001, perhaps like this. Come on. Yeah, this is good. This looks a little bit more like the Harz Mountains and this area. You remember, this is the SRTM dataset, nothing changed, just imported, and yeah, quite good. Okay, so we want to do the channel network here in these Harz Mountains. So we pick here channel network, and of course here the grid for the Harz Mountains and not for Eschwege. Elevation, yeah. Flow direction, yeah. Create for the channel network and the direction, and then the initiation grid should be, of course, set. This is most important. Divergence you can set, it's good, but the tracing rate we cannot set. Minimum segment length, it was, I think, when I remember this well, we did it with 5. Yeah, it should be good, like this. I say okay. Now it calculates a little bit more because these are, yeah, this is a little bit more tricky. These are 200 by 1200 points because we have for 1 degree, this is 1 degree in east-west and 1 degree north-south. We have 3,600 seconds, of course. And if we have 3 arc seconds width, then it is 1,200 in east-west and in north-south. So where is it? Of course, once again with data and channel network, and I put it directly upon directly on top of my grid. Say okay, and if I zoom in, this was no good idea. Okay, it seems to be to happen with the or to have to do with the minimum segment lengths. I will delete this one again and do it again. can zoom, or if you want to zoom to this whole area, then you have here up here at the bottom, zoom to full extent. Okay, once again. So this is where everything is clear, and here I use 10 instead. Okay, let me have a look if this works better. Otherwise, I take out the divergence. Oh, we have 3:30 already. It's late in the evening in Chennai. Sorry for this. What's that? I have to take out the divergence. I don't know. It must be the divergence. Yeah. Okay, so I made this mistake also for Ashley. So here you see a little bit also of the mistakes that are here in the SRTM data set. Yeah, you see here, by now it works also with the Z values somehow. No, it's the I have to click on on my data set, and then I get the set values then. Okay, so this means if we zoom in here, for instance, here is a gap. So here we have the creek coming down. This is clear. Everything is okay. But here we have a gap in our creek, and the question is, where does it come from? And we zoom in, and we see down here the set values. We see we come from 338, and then it's going up to 340. And if we look there, 49, the valley is there, but not the flow of the creek. Yeah, down here it works again quite well, 300. But here is a small hill in the valley. Of course, this may be that there are bushes and that the radar measured the bushes there. It's no question, or that there are some trees covering everything. But this has not been extincted here in this data set. Yeah. On the other hand, I must say this is a very nice data set. Yeah. It helped us a lot, really a lot, for our projects. Okay, so the next thing we can model, on the one hand, channel network. The next thing we can model, for instance, and perhaps I will try again the channel network without divergence with the other data set here. No sinks. Create. Initiation grid has to be set. But this time I will not set the divergence, and I leave it with 10, and I say, okay, let's see. So, wow, which one is number 5? And on top of this, no, this here. Yeah, the divergence was the wrong button, or the wrong entry. So it works quite well if we calculate here without divergence. Okay, so let's have a look, for instance, for this creek, to get, for instance, the catchment area. It would be nice if we can outline the catchment area from a certain point on upstream. Yeah. So, for instance, for this area here. Is it the same area? No, it is not the same. No, this is this area here. Okay, there it will be a little bit more tricky, but we will find it, we will get it. Here it will be good. Okay, so yeah, we should zoom in here. So this is with the no sinks, and we can calculate the so-called upslope area automatically. So this is the catchment for a certain point in our grid. And I will try this here with the methods that we have. So it is in hydrology, and there we have the upslope area interactive. Yeah. Just to show you what is possible, perhaps, hopefully. Sync roots. Create. Convergence. I'll try it with this convergence here. It should work, but perhaps not. So by now, interactive tool execution has been started. So I have to do some action. I pick this here, and perhaps I will start I'll try to get the upslope area from here. Yeah. Oh, this was not successful. Okay. Because if I pick the wrong pixel, then of course this may be somewhere on a hill or something like this. And from there on we have no upstream area, no upslope area. I'll try it here again. No, what's that? Oh, I have to stop it. Okay, and set parameters again. This is okay. Convergence. What's before that? Roots. Okay. This has to be created. Okay, but here maybe also something a little bit wrong. Let's have a look if this works by now. There I got some very small area. But of course this is, yeah, here I got it better. Yeah. So this area here, this upslope area seems to be very small. But I can export this here, this upslope area. Of course, once again with the export functions with the grids. While other runs, okay, I have to stop the interactive procedure. Yeah, and I want to export this, and grid system should be this one is correct. Upslope area 8, and sorry that it's too fast by now, perhaps. Slow. Okay. Okay. So let's have a look if we get it. Yes, upslope AC. Okay. So it's in this area, and I check that I will get Have a look. It's this here, and I try to get the 0. So black to white. White to black, perhaps like this. Yeah, but I don't get it. Don't get the white transparent. Oops. So now we see this. Now it should be a bigger area. So it didn't pick all the area here, or outline all the area, the upslope area from this point here. So this has to be done a little bit more thoroughly and more in detail, and the pixel has to be picked very correctly here, so that this outline or this upslope area also works here. But you have seen at least these tools are available, and they, in general, they work, but it will be perhaps a little bit tricky sometimes, and you have to insert, or you have to get a lot of input, manual input sometimes. Okay. So SRTM dataset we have imported. We have seen visualization in 2.5D. It is called 3D, of course, but in the end it's only one surface. Although Saga is capable of visualizing several surfaces one upon the other. This is possible, but they are in the end also flying carpets. It will not create volumes somehow. Okay. Slope, no, we didn't calculate the slope, but the streamlines, the catchments, I tried. The streamlines were quite okay. I think you saw this, how it works, that it works. With the upslope area, you only saw that it works. And yeah, also how, but not in a precise way by now. Okay. Any questions? I think you are all tired. I think it has been a lot by now, and yeah, not easy. Okay, no more questions. So it's a big topic it has been a big topic for today. A lot of parts coming from the remote sensing up to the regionalization, and then also this interpretation or this modeling with this with all this background. Please play with this, yeah, instead of playing with the PlayStation or something. It's nice to play with hydrological topics and hydrogeological topics. And here these instruments, these really nice open source tools are very helpful, and it's as you saw it from the 2.5D visualization, it's also nice to work with it. You have something also for the eyes and to see, and therefore, yeah, this is quite, or perhaps also for playing around a little bit, it's quite good. On the other hand, I have now another topic for you, for the, once again, for the Germans in the afternoon, for the Indian participants here, perhaps tomorrow in the morning. which is going around groundwater protection and vulnerability. It's around about 1 hour, and I will upload it by now. Yeah, I have to. I didn't upload it up to now. I have to, but I have saved it already. So let me have a look. Where has it inserted? There. I create a link and I copy it. Groundwater vulnerability. A very important topic, especially for water supply, but also for some agricultural questions and so on. I hope you will enjoy it. There are a lot of concepts, and these concepts were developed over the last nearly 50 years, no, 40 years, something around it. Yeah, for hydrogeological mapping, this is a quite interesting topic because you have to work with GIS tools to get this mapping done. Otherwise, you cannot implement these methods. And it's preferably done and not with vector methods, but with raster methods. And we should see or look for the possibility to calculate with rasters tomorrow when we start. And you will see it is a little bit different from vector handling. You can also work on groundwater protection and vulnerability topics with vector data, but then on a point level. Yeah, then you have for each of the points all the attributes, and you can calculate in the attribute table with these for each of these points the groundwater protection or vulnerability, whatever methods you use. On the other hand, with raster calculation, it is pretty straightforward. But it's a little bit tricky to do this, and we will see this tomorrow. Okay? So, if there are no more questions, have a good evening, have a good night, have a good morning, so that we can meet again tomorrow and continue with these topics here, yeah? With topics of raster calculation. Okay, see you then. Hope you enjoyed it. Bye bye.
Ich habe nur Tschüss gesagt. Stimmt.
Ah, tschüss.
Super hero, no la 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 la, super the art super hero. Let's play again. One, two, three. One, two, three. Go, go, go. The person talking and the raindrops came on our kitchen. We were narrow in many suburbs. But to look at me. Okay, two little things standing there.